All right, here we go with Unit 3, Part 2. More components. And this is not the most exciting and dynamic subject to cover. So I want to start with tying this to a particular problem that I hope will give us some context on this. It has to do with just a vehicle I worked on this weekend, 2009 Corolla, something basic. Um, Came to me for a crank no start, which means get in, turn the key, shana na 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 na, engine will just crank. And when I actually went out to verify that concern, it actually fired up. And then it kind of stumbled and rumbled and and died. Then I went to crank it, and it cranked na 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 na, nothing. And then I was kind of like, all right, so I verified it. But it is weird. It started and then stalled. So then I gave it a little time, and I came back and checked it out again. And what I found was it it was an intermittent, right? Sometimes it would start and sometimes it wouldn't start. And so my first thing is this sounds like an electrical problem. So this is an engine performance concern, really. A crank no starts engine performance. A no crank, like you get in and you turn the key and it doesn't start, that would more be an A6 electrical concern, like a starter, battery, right? But a crank, sha-na-na-na-na, but a no start, that's more engine performance A8. So the fact that it did start, and then when it died, it didn't die boom instantly. It kind of stumbled and fell on its face and started to run a little bit, and then eventually died. If you ever run out of gas, that's what the engine sounds like, and that's what the vehicle does when you're on your last few little drops of fuel, and it gets maybe just a little bit more gas, and it tends to be a little bit more gradual. So um, it sounded like it was starving for fuel. Compare that to if it's like, for example, an ignition problem. A coil a coil works and it doesn't work. It'd be like everything's fine, bang, it's dead, right? Or if that's a crankshaft position sensor, right? So there's a lot of these concerns end up being electrical. But electrical is a subject where we learn how electricity works and the components and how to test them, right? But don't forget, we need to apply these concepts to actual problems, right? So this one was engine performance. And just the fact that the way it sounded made it sound like fuel, the down and dirty way that I'm just going to do this is I pop the fuel line off and I crank the engine over and I look for fuel to go flying out of there. No fuel came flying out. So I said, oh, okay, sounds like the fuel pump's probably not working. I couldn't hear the fuel pump, but those Corollas are quiet. So I went ahead, and where this fuel pump is, you got to pop the back seat off. Pop the back seat off. Put a little screwdriver on the top of the fuel pump, fuel tank area, put it to my ear, reached up, turned the key real quick so it would crank, right? On those, the fuel pump runs while you're cranking. It doesn't necessarily run with the key on only. And listen, no fuel pump. Fuel pump's not running. All right. So instantly, this engine performance concern is now just simply an electrical problem. If the fuel pump's not running, the fuel pump is the load in the circuit, right? So just had to test a motor, which is some of the stuff that we covered in part one, right? So just applying part one. The other thing is, if this car is out of gas, it's obviously going to do that type of thing, right? So how do we know if a car's out of gas? You're going to check the fuel gauge, but can you trust it, right? So we'll even discuss if this was an engine performance concern for a crank no start and it was starving for fuel, but I were to put my screwdriver up to the fuel pump, or a stethoscope would be better, and listen, and the fuel pump was running, but there was no fuel spraying out of the line. I think either it's out of gas or there's a fuel filter restriction or something, right? So again, which if the fuel gauge, this one is reading a quarter of a tank. If the fuel gauge reading a quarter of a tank, but the fuel level's low, guess what? That's still an electrical problem. But that would be the fuel level sensor type of issue, right? So as we cover this, keep in mind, we got to apply some examples to how the electrical concepts and components and whatnot will be applied specifically to problem cars. This was just a crank no start, right? So yeah, I go ahead, next step, check 12 volts. The pump is getting 12 volts. That tells me everything in the circuit giving 12 volts to the pump is good. The pump is getting ground. If the pump's got 12 volts in ground and it's not working, it's a pump motor. Pump is no good. So real simple. Put a pump in there, boom, fire it up, it's done. No problem. Complicated jobs, if electrical based, if you understand electricity, you know how to measure, you know how to test it, boom. Complicated jobs, no big deal, easy, no problem. So okay, setting the tone with that, we'll jump into the part two, which is going to wrap up electrical and really get into electronics. The first thing being, let's start with components here, resistors. um, Resistors could be something very simple, or they could be something a bit more complex. So if we were to look at a more simple resistor, this is a resistor, yes. But I'm going to start with this because this relates to that real world application Corolla. This is a variable resistor. This is what a variable resistor looks like, as like a diagram. You may see them like this on the diagram. This is kind of like a fuel level sensor, right? So obviously in this vehicle, I look at the gas gauge. Gas gauge reads a quarter. If I look at the gas gauge and the gas gauge reads a quarter, and then I go ahead and, sometimes it's not the most technical methods, but I'll shake the car and try to listen for fuel sloshing around in the tank. And I heard it on this one. So I said, yeah, a quarter is probably accurate. But this just comes from experience, right? If I shake it and it sounds like it's empty, there is a chance that there's an electrical issue causing that fuel level sensor to read incorrectly. So like this one right here is perfect. Where this arm is about a quarter. It's just below a quarter. It's exactly where this Corolla was, right? As the vehicle is empty, this is going to be attached mechanically to an arm and a float. And the float's just a hollow plastic piece that's like kind of like a buoy, right? As the fuel level goes down, this sweeper arm will go down eventually to here. And that would be as low as like a half of a volt. That's going to tell your fuel gauge, hey, be buried right on E. That's how you know you're out of gas, right? If you put 5 gallons in it, you're probably going to have that float up. And, if it's a 13-gallon tank, maybe you're going to end up around here, just a little bit between a quarter and a half, right? So this is a variable resistor, but if you put it into a component, it would be a fuel level sensor with an arm hanging off it and a float that's going to float on the fuel level to indicate how much fuel is in that tank, right? So if I were to have troubleshooted that and thought that that was the problem, here's how we would do it. Let's say it's reading half all the time. Half all the time would actually be about 2.5 volts on this variable line. I'll explain how that works. We send 5 volts to the level sensor. That 5 volts is going to basically drop until it gets all the way down here to 0. And we have our level sensor attached to this wiper arm, and the wiper arm can never go all the way to 0 volts, and it can never go all the way to 5 volts. It'll go something like a half a volt at the lowest to about a 4.5 volts at the highest. So if I'm at the middle, that would mean that this is going to be reading about 2.5, right? The voltage coming through is going to drop, and then the resistor arm is just going to be reading what the voltage is here. The voltage starts at 5 and it drops all the way 4, 3, 2.5. That's where middle of the tank would be. 2, 1, and a half, or close to 0. Cool. So this resistor varies depending on where the fuel level is. 0.5 volts, 2.5 volts, 4.5 volts would be full, right? So I could basically probably have to look in the tank or make an approximation of how much fuel. But if it's reading half a tank, and let's just say I go to the gas station and I fill the thing all the way to full, well, and it's still only reading 2.5 volts, I could actually do some troubleshooting on this electrically, make sure I've got 5 volts, make sure I've gotten ground. And if I'm reading 2.5 volts, that means that this is stuck at this point. It actually could be something mechanical, like the arm is stuck. Let's say we took it a different way. Let's say it read empty all the time. and you put gas in it and you put more gas in it and you filled it to the top where fuel was spilling out of it and it's still read empty, that could be, ready, if it's full and right here this resistor grid has an open in it, it could actually cause this variable to read zero because there's no contact, right? This resistor grid is a carbon, like a contact point. And if the carbon was wiped off of this variable resistor, you'd be getting 0 volts if this was supposed to be reading full 4.5. So you'd be like, oh, if the fuel gauge is inaccurate, it's got to be a bad fuel level sensor, right? It's the variable resistor. Sell it. Are you sure? Because guess what? If we lost our 5-volt reference, there'd be no 5 volts here. That means that the variable resistor, this signal voltage that should sweep, it's going to be 0 all the time because there's no 5 volts. So an open in the 5-volt circuit would also cause this to read empty. So we're not sure that it's the level sensor. It could also be an open 5-volt reference. So we got to get down to that sensor and actually measure and verify the voltage. Cool. Or what if we had an open on this blue wire, this signal voltage wire? That would also read 5 volts. That would also read 0 volts. That would read empty all the time. Right? So you're going to notice a trend when we talk about these components and applying them to a specific situation and how to test them and, give examples of why we test it this certain way to give you an understanding, right? So something as simple as, the vehicle came in with a crank no start and the fuel pump wasn't working. It could be the pump motor. It could be that it's out of gas. That's the mechanical aspect. But what's common, it could be the wiring. A lot of times it could be like the ECM because the ECM commands the pump on. And if the ECM isn't giving the signal to command the pump on, you don't know if you're selling a pump, a wire harness or wire repair, or a module ECM. And in the case of a fuel pump, there's even the relay and the fuse and even, other stuff. When it comes to this fuel level sensor, keep in mind, this measures the level of fuel. So if you have an incorrect fuel level concern, it could be the sensor, but it could also be, again, the wire harness, a wire repair, or in this case, this variable circuit right here actually sends it back to the instrument panel. A lot of times there's some sort of a computer, we'll just say loosely, and that's actually going to go back to what we covered last time. That is going to control a stepper motor, and the stepper motor is going to go ahead and tell the needle where to go, right? So if you had 2.5 volts on that fuel level sensor and 2.5 volts was going on the blue signal wire and it went to the instrument panel, that this motor control module would interpret, hey, 2.5 volts coming from the fuel level sensor. That reads half a tank, and it will control this motor. It'll give 12 volts and ground to the motor, and it'll go step, 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 right until the needle's at the halfway point. Cool. So you're seeing both sides of it now. What we covered last time was the output, and this just indicates whatever the fuel level sensor information gave, whatever the fuel level sensor gave to the motor control module. Make sense? So then if we were to go back to the fuel level sensor as a variable resistor, we're talking about this whole issue. If we had an open 5-volt reference, that's going to give 0 volts on the blue wire. That stepper motor control module is going to see 0 volts. It's going to be like, oh, that's empty. Boom. That would be a bad sensor, and or if it would be in the harness, it could be that, right? But let's just say all this was reading correctly and it sent 2.5 volts on the signal wire, but that stepper motor was no good and it had no ability to move the needle up to half. You could actually have a needle that reads empty all the time caused by the stepper motor, which means we'd be selling an instrument panel. Or again, it could be that variable signal voltage wire, or it could be the 5-volt reference wire, or it could be the actual variable resistor, right? So when we talk about these components, just understand it's not quite as simple as you'd like it to be. Like, hey, when my gas is full, my gauge reads 0. What's wrong? Be like, I don't know. The cars don't talk to me. For me to really know, you got to understand the circuit, right? You got to understand how this variable resistor works. You got to understand it gives a signal to a motor control module. You got to understand the motor control module then tells the stepper motor what position to be in. You need a good stepper motor. You need good wires between the stepper motor and the motor controller. You need good wires between the motor controller and the variable resistor signal voltage. You need a good 5-volt reference. You need a good ground. You need a good actual variable resistor. And you also need that float and the arm to be free. It can't be bent and stuck on the side of the gas tank because it was installed wrong, right? So just a simple problem has a lot of potential, causes. And so if you think about that, to just perform a basic diagnosis for a fuel level sensor, you're going to spend time. You're not just going to look at the car and be like, tell me, baby, what's wrong? And have it be like, it's the open 5-volt reference. Like, they don't do that. So therefore, for us, what we do, we would verify the concern. Let's say in this case, the fuel level is showing empty and the customer says it's full, and you shake the tank and you're like, oh, it sounds full. That would be verified. From there, what do we do? Well, I'd probably say we should start by checking this fuel level sensor. So you could look at it on a scan tool and that would tell you what the computer is getting from here. But if the computer's showing zero fuel level, then you physically are going to have to access this sensor, which means you're doing what I did, pulling the back seat, pulling that panel, and that it's got a little access panel on the Corolla that's like glued on with butyl. It's kind of a mess, and you got tug and pry, or like on some vehicles, you got to actually probably drop the gas tank, which can be a job in itself, right? Then you got to get access to this connector. Okay, so a little bit, we're going to actually talk about connectors. You got to access the connector. Then you got to know which terminal is the 5-volt reference, which terminal is the signal, and which terminal is the ground, right? And then we got to verify. If this has got 5 volts, that means the 5-volt reference is good. If this has got ground, that means the ground is good. If this variable voltage being put out is 0 volts, the sensor is bad. Assuming that the fuel level float is not stuck mechanically inside the tank, right? I always got to specify that. But if that's free to move and it's reading 0, it's a bad sensor. Done. But what if the voltage coming out of the sensor is like a 4.2 volts? And you'd be like, well, that sounds good. Why isn't the gauge reading? Well, then if you're getting 4.2 volts here, you don't know if it's making it all the way to that stepper motor controller. It could be an open in this blue wire, right? So then you'd have to check the blue wire coming out of the sensor. And if it's 4.2 volts, then you got to follow the blue wire and check it where it goes into the instrument panel. And if it's 0 volts over there, it's an open wire. So then you got to sell wire repair or wire harness. But if it's 4.2 volts coming out of the sensor's good, and it's 4.2 volts going into the module, into the instrument panel, then the wire's good. The instrument panel is getting 4.2 volts. Why isn't it reading full? Then you're probably going to sell an instrument panel, right? So again, at the most basic of what we do, we take a problem, we understand all the possibilities, and we go and we test to prove what's good. And then eventually we'll either prove that everything's good except one thing, or we'll confirm that something is bad, which is better, the ideal. We can confirm and prove that it's bad. And then we're selling the thing that's actually bad. Okay. But it takes time, which means we're charging diagnosis. And if, some places want to say, oh, we do free diagnosis, but I don't think so. We all go to work and we want to get paid. Need to get paid. You need money to survive. So if you go to work and you're like, oh, let me diagnose this for you, what I'm going to do is pull your back seat out and pull this panel and look up a wiring diagram and put my meter lead here and here and here and there and then I can actually diagnose it. You're going to spend a bunch of time and somebody's got to pay for that. Now you could have a company that's going to eat that time and just pay you out of their pocket to try to get more business. But I'm going to tell you, that's not a very successful business plan typically, because it's very common. I'm going to introduce you to a hypothetical character. His name is Mo. Mechanic. Mechanic works on the side. Mechanic doesn't do diagnosis though. He just replaces parts that other people diagnosed, right? So if you want to bring this to a shop and say, hey, I want free diag, if you think they're going to put a technician on there and the technician's going to make the measurements and do the test and then be like, yeah, you need a fuel level sensor. And then the customer's just going to grab that and roll out and give it to Mo because Mo does work on the side cheaper under a shady tree in the moonlight. Um, the shop that's offering that free diagnosis is probably going to be out of business, or it's going to be free diagnosis as long as we do the repair. And sometimes they'll even do like a, if your diagnosis goes towards the repair, most of the time that's just masked, right? So if you look at, typically we're going to charge an hour minimum diagnosis fee. If I look at that hour, right, and I verify the concern and I decide I think it's a fuel level sensor problem, and next thing you know, I pull the back seat out and I pull the panel out and I start probing and testing and I verify that it is a fuel level sensor. I mean, truthfully, I've already got the back seat out and stuff. I'm a little closer to doing the pump. We may say, hey, that fuel pump bill's at 2 hours and that's plus 1 hour diag, but we're going to put your diag time towards the repair. Maybe we end up only billing them 1 more hour because we're already pretty close to the pump. I could see some sense in that. I could also make an argument for not doing that, but that'd be ethical. That'd be good to do. But what I don't see is, you're going to do probably what the shop's going to do, honestly, is they're going to say, yeah, you're going to pay an hour diagnosis at a shop rate, on the low end right now, that's like $125, but most dealerships are about $200. You say you're going to pay $200 towards your repair. And then they're going to show let's say a 2 hour labor at 200 an hour is $400 for the replacement of the pump, not for the diag. So you got 200 for diag and another 400 for the actual labor. So you're up to $600 in labor. And then let's say that the pump is $300. You're at a $900 job, right? A lot of times what they'd probably most likely do is be like, yeah, we're going to charge you $200 in diag. And then when they call back, oh, yep, yeah, your pump to replace that pump, it's $900. And it would be $1,100, but we're going to give you the free diag. So it's only be $9. Or they might say something along the lines of like, your diag, we're going to put that towards the repair. So it's only an additional $400. It would have been more, but we put the diag in there. But did they really? Like, you paid $200 for the diag and you paid $400 for the labor, you're still paying $600. So is the diag actually free? Now, if, they can spin it anyway, right? But the point being, it's not that hard to hire somebody to replace the fuel pump. It's much more difficult to hire somebody to diagnose it as the fuel pump or as the fuel level sensor, or determine it's this wire, or determine it's this wire, determine it's this wire, right? So understand, everybody needs to know, diagnosis is more technical, more difficult, and requires more skill than replacing parts. So free diag, I don't think so. I just don't. Typically, the people doing the diagnosis are making more money per hour. So if they're not willing to have a cheap person stuff a fuel pump in it, why would they be willing to have an expensive person performing more advanced diag who has a higher education, more experience, probably certification, right? Probably has a lot more invested in tools and diagnostic equipment, right? I don't think so. So with that being said, as we go through this, understand it's going to be technical and it's going to be kind of difficult. But if you really want to be at the top of the game, you got to be able to do the diagnosis. Okay. And the diagnosis is going to be, a lot of it's going to be electrical. So that's why I justify being very thorough on this subject, right? So we talked about a variable resistor in an applied manner. Let's look at resistors in general. Here's your first type, fixed resistor. A fixed resistor is just that. It's a fixed value. So if you have a 25 ohm resistor, it's just a 25 ohm resistor. That's important. It's valid, but it's 25 ohms today. It's 25 ohms tomorrow. It's only ever going to be 25 ohms. It doesn't change with position. It doesn't change with temperature. It's just 25 ohms. That could be two types. It could be a wire wound like this one. So if you look at this wire wound, That's going to be like, when we talk about coils of wire, that wire does have a resistance. The longer the coil of wire is, the more resistance it's going to have. This is just a way to wrap a wire around and around and around and make it longer. And there will be a certain amount of resistance in here. The longer it is, the more resistance there's going to be. So it could be just literally a long length of wire. And a good example, that's the old school blower resistor. They had resistors like that. They would get hot and fail and break, and then you'd have it open. They fail. Another type of resistor that's much smaller is going to be this carbon resistor, and that's going to be one of the more common with like ECUs will have a lot of resistors, right? And these have colored bands, and we are going to cover those. But this is an example of a carbon resistor. They're both fixed, right? Let's jump into a variable. You've already heard about a variable. That fuel level sensor works, that's a potentiometer a lot of the time. So we may not always call the sensor a potentiometer, but if you understand a potentiometer and how a potentiometer works, you can really begin to understand how to do the diagnosis of all different types of potentiometers. This one, for example, is a throttle position sensor, right? The way we diagnose the throttle position sensor is the exact same as how we would diagnose that 3-wire fuel level sensor, right? This one might have one extra wire. I think this is a doubled up redundant TPS, but we'd have like a 5 volts coming in, a ground on the bottom, and then depending on the throttle position, we'll have somewhere between a 0.5 volt and a 4.5 volt because that same carbon resistor grid that's in there, right? A variable resistor. We test it the same. Now, the potentiometer and the rheostat, they're very, very, very similar in how we diagnose, but they're very, very, very different in their function. And we're going to be building circuits on these circuit boards. And when we build these circuits, you're going to have a potentiometer and you're going to have a rheostat. The potentiometer is really a sensor. They typically work on 5 volts in ground, and they'll provide a small voltage back to an ECM. They don't carry current. They don't carry a load. It's a very small current flow because it's computerized electronic circuits, right? The rheostat, for example, that's like a full-blown dimmer. That can carry a bunch of current. You could send full 12 volts through there and have the rheostat dim the lights, right? So if you wanted to dim the most common would be like your interior instrument panel lights on an old school car, we'd have a rheostat mounted to the dash and you turn a knob. And that rheostat would actually be a resistor that would be taking current and it would actually get hot. And you could say like turn the rheostat to the middle, and that would be dropping 6 volts at the rheostat, leaving only 6 volts available to all your instrument panel lights, and that's how they'd be dim. Then you turn the rheostat, up or down or whichever way is more bright, and then the rheostat might only drop 2 volts, and then you get 10 volts available to your lights, and that would make them more bright, right? So the rheostat is actually in line with the load carrying current, whereas the potentiometer is usually a sensor that's indicating position. And then, if it's a newer vehicle, we don't use rheostats to dim the lights. What we'll do is we'll use a potentiometer, and the potentiometer is just a sensor that gives a signal back to the control module, and the control module will from there pulse the LED backlighting at a varied rate, right? So at the very end, we get into duty cycle a bit. If the potentiometer says dim the lights, turn the lights down low like that, maybe that's going to be like a 10%. That would be like a 0.7 volts or something. That's going to send a 0.7 volt signal to the ECU, and the ECU is going to say, give me just like 10% on time on those LEDs and 90% off. 10% on, 90% off. Now, to your eyes, you don't see the flash, but if they're only on 10%, trust me, it's not going to make a very bright light. That would be a 10% duty cycle. Then if we turn the rheostat up to 2.5 volts, that ECU would give a duty cycle of about 50%. They'd be half on and half off and half on and half off. That's going to be like your middle setting. Then if you wanted like full, you might turn this rheostat all the way up to like a 4.5 volts. That's going to probably give 99% duty cycle. 99% on, 1% off. 99% on, 1% off. That's going to be as bright white beaming as those LEDs can be, right, on your instrument panel. So this is electronic, goes to the computer. The computer will generate a duty cycle, whereas the rheostat straight up, the exact electrons that are going to the bulb got to go through the rheostat first. Diagnose, same. This is going to get a 12 volt or a 5 volt and a ground, and it's going to have a third wire for the variable, like the signal. This is a lot of times going to get a 12 volts, and depending on this varying, it's going to get a certain amount of voltage back out. Some of the rheostats are 3 wires, so you get a 12 volts in, a ground, and then the middle wire will be actually what's carried out to the bulbs at 6 volts or 10 volts or whatever. The diagnosis is very similar. If you take a potentiometer on these circuit boards and you try to wire it in like it's a rheostat, you'll burn the potentiometer out, right? Rheostats can handle 10 amps. Potentiometers are used to like 0.1 amps, right? 100 milliamps, very little. Cool. So these are examples of the variable resistors. You can check the resistor with ohms. You can check the variable resistor with ohms, but the variable resistor will change with something. The movement, the throttle position, the fuel level, whatever, right? But the resistance is varying. Technically, you could check them both with an ohm meter. It's common though that we'll use a voltage drop and we can calculate the resistance, and we'll voltage drop this to spec, and we can tell what the resistance is without disconnecting it and measuring with ohms, right? We can see how much voltage dropped across it. That'll tell us a lot. Now there's one more here that's a variable resistor, but it's a special type. It's called a thermistor. And a thermistor is, we're gonna generally assume NTC, which is negative temperature coefficient. They do have PTC transistors, but they're just, or thermistors, but they're just not common. So we're gonna focus on NTC, negative temperature coefficient. Almost everything in nature works the same. When you get wire hotter, the resistance goes up. When you get a lot of conductors hotter, the resistance goes up. Thermistors are freaks in nature. They're backwards. When a thermistor gets hotter, the resistance goes down. You're like, what? Whereas when a resistor gets colder, a normal conductor, when the resistance goes down when it gets colder. On a thermistor, when it gets colder, the resistance goes up. They're backwards. However, that's kind of a good thing. They're very consistent. They have a very linear resistance change with temperature. So we tend to use those in temperature sensors. Like, for example, ECT is engine coolant temperature. We're going to shove a thermistor in the coolant, and the thermistor is going to change resistance, and the ECM is going to monitor that change through a voltage drop in a voltage divider circuit and be like, I put out 5 volts and 2.5 volts was consumed. That means that's got the exact same resistance as the internal resistor. They could interpret that as that'd be probably about 100. Let me think, about 100, roughly about 100 degrees would be 2.5 volts. Right. So, and they can vary, but the ECM can monitor how much voltage drop is occurring across this temperature sensor in a weird way, which I'll explain a different time. But essentially, it can tell what the resistance is of that thermistor through voltage drop. All right. So for now, we'll talk about it as measuring resistance because, that's the way you bench test it. But in the car, actually, it kind of make more sense to measure the voltage drop of the resistor, of the thermistor, and then you could, tell what the temperature is, right? So if you had this thermistor reading OL is not overload. OL is out of limits. And remember, your meter in ohms, it can measure millions of ohms. It can't measure billions, trillions, quadrillions, hectillions, millions. It can't measure that. It can only measure just millions. So if it's reading above millions, it's out of the limits, right? So if I go ahead and I try to measure the resistance, put my red lead here, put my black lead here, and it reads OL, that means it's basically open. It's got more than millions of ohms. It's got, who knows, tons and tons of way more than millions of ohms. That's going to indicate -40 on the scan tool, thereabouts, -38 to -40, right? So if something has if a thermistor has a lot of resistance, that's a very low temperature. So what's crazy is like if I pull a car in and I look at the code and let's say it's got an engine coolant temperature circuit open or performance or something, and I look on live data and it shows the temperature as -40, boom, I got it. I'm like, oh, that's open or extremely high resistance. I'm looking for disconnected connector. I'm looking for wires chewed. I'm looking for, corrosion on terminals, right? Anything that would add resistance to the circuit will make it read a lower temperature. Well, it's also possible it really is -40, but it ain't possible where I'm at. -40 here? I don't think so. I felt -20, but it was back when I lived in New York. -40 is wild. These don't measure wind chill, by the way. This is an inanimate object. It doesn't measure wind chill. So I'm talking -40, straight up -40. There's not a whole lot of places that are going to experience that. North Dakota, maybe Montana. That might be very rare there. Alaska, northern Alaska, that's probably happening every day, right? But if I see -40 and I know outside is 60, I'm looking for corrosion. I'm looking for excessive resistance. Cool. Now, the other way is true. If there's not enough resistance, like in other words, let's say it got shorted. Let's say you took these two wires and you shorted them together. That would read full hot, which would be like 270 or 300 degrees or so, thereabouts, right? So just understanding electrically how the thermistor works, my diagnosis is going to go much quicker for temperature sensors, engine coolant temperature, intake air temperature, cabin temperature, right? So transmission fluid temperature. If I were to zoom out and be like, hey, this is an electrical lesson, that's just kind of true, but ECT and IAT, that's engine performance, that's A8. If it's a transmission fluid temperature circuit, that's A2. If it's a cabin temperature sensor, that's going to be A7 electrical, right? I mean, we could pile on different examples of where we're measuring temperature, and put it into a bunch of ASEs, but understand it all comes back to A6. It all comes back to this understanding. This resistor is going to vary with temperature. I'll even tell you, if you understand thermistors, you never know how it could how it could benefit you. So, fun fact, have you ever seen the price of a nice stainless steel, French door, fancy Samsung, in my case, refrigerator, like a nice one, nice stainless one? Someday, some of you will be, maybe you already are, maybe you're already, married, or, have a family where you're looking for, making your home nice, where you can be comfortable, where you spend some of your time. You're going to look for a refrigerator. You're going to roll into Home Depot and Lowe's, and you see the price tags on those things, $2,500, $3,000. And you'd be like, what? For a fridge? That's crazy. Well, same with me. I'm always looking for a deal though. And I found somebody selling a fridge still wrapped in plastic. You could tell somebody unpackaged it or something, but like it didn't have food in it and stuff like that. And it kind of seemed like a little sketchy, but like I'm down. I'll get involved, because it was $800. So you're talking about like less than half price. Like I'm going to go. So I meet these people, look at the fridge. It looks perfect. They don't offer, I can't plug it in or anything, but I'm like, yeah, I'll take it. So I buy it, bring it home. Looks good. I'm the hero. My wife's like, wow, great job. Hope you got a deal. And I'm like, you don't even know the deal I got or how I got it. That's why I got a truck on standby, ready to go. But I got it home. Everything seemed fine. I put the milk in there. The milk wouldn't even last a week. It was like 5 days. The milk was rotten, stinking, sour, nasty. And I'm like, that's weird. Maybe it's Costco. Maybe something's wrong with that. Tried some different milk, same thing. It wouldn't even last a week. And I don't have time to go shopping multiple times. I could barely go shopping once a week. I don't have time for that. So I'm sort of like, all right, something's up. Maybe the fridge isn't as cold as it thought. So I look at the front of it and I turn it down as low as it'll go. I can turn the fridge side down to 34. Can't turn it below 32 because that would be freezing, but it can go as low as 34 on that. I don't think I could do 33. But if I set it to 34 and I open it, it feels cool, but how would I know if it's accurate? Right. So kind of similar with these temperature sensors. How would I know if they're reading accurately? Well, there's a thermometer. So I put a thermometer inside of the refrigerator, just like you would to test these, to actually measure what is the actual temperature of coolant or air, or in this case, the inside air of the fridge. And I shut the door and I came back an hour later. It was 50. So I had it set to 34, but it was actually reading 50. Right. So the real temperature was 50, but the indicator said it was reading 34. So think about that. This thermistor is in 50-degree air, but it's giving me a high enough resistance to act like it's 34 degrees. So the whole time the fridge thinks it's 34, it ain't that cold, it's 50, and that's why the milk is spoiling. So I'm like, well, not a big deal. I understand thermistors. I paid attention in class. I gained a lot of experience in the field. So I'm like, well, let me troubleshoot the temperature sensor. And I got at the thermistor, 2-wire thermistor. I actually was able to download a service manual for the Samsung, whatever the tag is in the door. And it gave me a chart, at 50 degrees, it should have, I'm going to throw a fake number out there, or at 34 degrees, it should have 100 kiloohms. At 50 degrees, it should have 80 kiloohms. Well, when I measured the thermistor, it was reading 100 kiloohms, even though it was only 50. It had excessive resistance in the thermistor, right? I measured the thermistor directly. It wasn't that it had it in the harness or in the wire. I measured the thermistor, and it was reading at a spec based on the spec of the service manual. Said, well, it's got a bad thermistor. New thermistor, $8. I fixed that fridge for $8. That refrigerator should have been 2,500. I got it for $800, an hour of troubleshooting, and an $8 thermistor. So I'm just making a case to you. If you understand how this stuff works and you can actually diagnose it, I mean, you can do way better than getting a good deal on a fridge. You can make enough money to provide for your family, maybe purchase a home, maybe get a motorcycle or a cool car or something. But you got to actually get good at it. And it takes a lot of practice, a lot of study time, a lot of, you got to give it a lot of effort to understand it, right? So that's just a little mini lesson about thermistors. You can apply it in many different things, even refrigerators. All right, now let's roll it. So on these fixed resistors, I'm going to teach you something that's probably never really going to help you out, to be honest with you. These resistors, you can tell their resistance by looking at their colors, and they'll have a chart here. So band number 1, that's going to be this one, red. Okay, red 2, right there. Band number 2, green 2, green is 5. So 2, 5 is 25. And then the black is going to be the number of zeros. So in this case, black is 0. So 2, 5, no zeros, just 25 ohms. And then there's the tolerance. How tolerant is this resistor? Is this resistor tolerant? And I look at it and I say, oh, it's got 1% tolerance. That is a very intolerant resistor. I would like a resistor that has no band, and that's tolerant of plus or minus 20%. Or let's just say it had a silver band that's plus or minus 10%. If it had a silver band, that would be 25 ohms plus or minus 10%. So you're talking about 24.75 ohms up to 25.25 ohms. Is that right? 10%. No, 10% would be 2.5 ohms. Okay, so that would be 22.5 ohms to 27.5 ohms if it was 10, right? So the band color at the end is just to say it's going to be, I joke around about tolerance, but actually, if you were trying to build the space shuttle, you're probably going to shoot for a little bit of a tighter tolerance than plus or minus 10%. You're going to be like, yeah, give me plus or minus 1%. So that would be like a 25 ohm resistor would be 24.75 to 25.25. That'd be quite a bit tighter, right? So either way, this is how you could determine what the resistance is. Or you know what you could do? You could just measure it. So this is a good thing to know, but as technicians, honestly, like we don't usually set up our own resistors to control the circuit. It's just something you got to understand. So that way, when you see these resistors, you just know, hey, these colors mean something. If I had to, I could pull these off a chart and plug them in. But honestly, I learned this in class and I've done it 0 times in the field, but I learned it in class and I remember it from class. And so if I had a conversation with an electrical engineer, we could have an educated conversation. I wouldn't look like a total ding dong and be like, wait, resistors have colors and they mean numbers. But honestly, this is not something that's real critical. All right. So if you go on with resistors, remember, they're rated in ohms, they're measured in ohms. It's all about the resistance level. And basically, what they're going to do, the resistor would be used in a circuit to um, increase the resistance. So if we were to look back at that fun picture where the ohm is pulling the rope up and the amp, it's stopping the amp from going through. If you increase the resistance, it's like the ohm guy being stronger, it's going to make less amps. So if we want less current flow, less amps, we could increase the resistance. We could put some resistors in there. Also, the resistors will consume voltage. And so let's say we're trying to run LED. An LED can't run on straight 12 volts. You got to drop it down. I don't remember the voltage. It might be like 1.4 or something. So we could put in a certain resistor or multiple to consume, let's say, like 10.6 volts to leave 1.4 for the actual LED. So we can use the resistors in the circuit to control the current and to basically give us the voltage that we want. Right. So that's what, but we as technicians, we don't really set that up. An electrical engineer sets that up. What we're going to do is we're going to fix it when it's broken. And you may have bad resistors. If you have a bad resistor, they're generally soldered onto the circuit board of the module. So if there's a problem in the module, we're done. We're replacing the module. It'd be very rare for a technician to take a module out and take it apart and measure an individual resistor and desolder the resistor and solder a new resistor in. Now, there are people who do that, but that's not your normal technician. And it's definitely not your normal US based technician. And it's definitely not more where my specialty is, which is like the dealership. Like that's definitely not what we're doing. Cool, but it's a good thing to know. So this is just explaining what the colors are. And here's a bigger chart. And they have resistors with more bands and less bands. And it depends. There's a multiplier to get a really high resistance, or there's, the tolerance. And they even have temperature coefficient specs. And so, a lot of this stuff is great, but not real critical to fix a modern car today. Just be aware all these lines mean something. And if you did have to diagnose a resistor, you'd probably be following the service manual and it would give you a spec. But if you couldn't get a spec, you could do brown plus whatever color, black, orange. You could figure out what the resistance should be, and then you could measure it. 100 kiloohms, that's 100,000 ohms plus and a tolerance of 0.1%, right? So you get it. All right, cool. And that's all we need to say about resistors. Now, rheostats, like I talked a little bit about, remember, a rheostat is basically a dimmer. So if you were to go over to a wall in a home and you could move a dimmer, there's a good chance that's an actual rheostat. On a car, yeah, if it's like a 19, let's just say I'm going to pick a 1971 Chevelle, that could actually have a rheostat on the dash to dim the lights. And again, the way we diagnose it, you can measure the voltage coming in. It's probably going to be source voltage, 12-ish or so. And then by the time it goes through the rheostat, it's going to drop a varying amount of resistance depending on where the movable wiper is. and the amount of voltage that'll come out is going to depend on where the movable wiper is. And so let's say if the wiper is positioned close to the end of the coil, the resistance value increases, right? So if you have it at the beginning, it's not going to have as much resistance. Your lights are going to be more bright because the rheostat's going to consume a little less voltage, leave more for the lights. If you have it towards the end, that's going to be more like it's going to have a lot of resistance going through that rheostat. So your light's going to be very dim because more resistance means more voltage drop on the rheostat, leaving less voltage for the bulbs, right? So you just measure the resistance and sweep it. Sometimes they have good resistance, and then you get to a certain point and it's dead. It's got a dead spot. A dead spot's fairly common. They'd be like, oh, the rheostat's no good. Yeah, when I'm adjusting my brightness, when I get to a certain spot, they shut off. Like, it sounds like probably the rheostat most likely has got a dead spot. Cool. And then potentiometers, like we talked about quite a bit, very similar. You'll notice it's still got the wiper, but we moved to this point. It acts as a voltage divider. What that really means is the ECM has a voltage. It's most likely 5 volts. It's going to send it through a fixed resistor that's let's say 1,000 ohms. And it's going to go through there, and then it's going to go into the potentiometer, and the potentiometer's resistance is going to change with some sort of position sensor, such as throttle position. If your throttle position is, let's say, 1,000 ohms, if your fixed resistor in the ECM is 1,000 ohms and your potentiometer is reading 1,000 ohms, they're the same, right? So that would mean they each get 2.5 volts. That's what they mean by a voltage divider, right? So without going full crazy on what is a voltage divider, we mostly cover that in engine performance. I have a whole lecture on voltage divider circuit. Just understand it is carrying a small amount of current, but we're not using it to control a lot of amps to dim the lights. We're more using it as a voltage divider where we have a 1,000 ohm resistor in the ECM, and then we have a variable resistor on the potentiometer. And depending on how much voltage drops in the internal resistor, the ECM will measure the voltage afterwards and be like, oh, well, if it dropped 2.5 volts, that means the outside variable resistor must be 1,000 ohms as well. 1,000 and 1,000 with 2.5, it split it. And that would mean a half a tank of gas or a 50% throttle or whatever, right? That's all. It's in sensor format, period. Cool. The way we diagnose it's the same, like I was saying before. Measure, does it get the 5 volts in? Does it get the ground? And is it giving a correct varying resistance as you sweep it? Half a volts all the way down, 1 volt, 1.5, 2, 2.5. That's the midpoint, right? That's like the 1,000 ohms if it's a voltage divider. 3, 3.5. Maybe you get to where it should be 4, and all of a sudden it goes to 0. Boom, 0 volts. It would be a dead spot in the potentiometer, just like the rheostat. Cool. So we diagnose them similar. Capacitors is another fun one. Capacitors are, like we talked a little bit about capacitors some. A capacitor is a device that's going to store electricity. So for example, if it's your big boom boom system, a boom boom, a boom 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 boom, each of those booms of the subwoofer is, a lot of current going to an electromagnet moving a big cone, with making your subwoofer go a boom ba boom a boom ba boom ba boom ba. That draws a lot of power. And next thing you know, your alternator's doing its best and your battery's like, maybe not quite able to stabilize it. So every big a boomba, 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 your headlights start to dim when the bass hits. You're going to get pulled over. You're going to go to jail. But we could resolve this by putting a capacitor in. So when the boom, boom is not hitting, the capacitor's charging. But then when the big bada boom hits, the capacitor discharges and it stabilizes the voltage. That's exactly what a capacitor does, right? So most of the time I use the example of the car audio, but I do want to apply this in a way that's going to benefit you as just a repair technician, not like a 12-volt audio tech, right? So just keep this in mind. And this, capacitors have different specs. Capacitance is the measure of the amount of charge stored on each plate for a given potential difference in voltage. So if it has, the more capacitance it has, the more it can store inside of it, because it's probably gonna have more plates and bigger plates and whatnot. It can measure it in farads, but if you have a big capacitor, that would help this car audio. Small capacitors tend to have a different job. So, like for example, I've used this before, airbags. If you get in an accident and you get hit so hard that your battery flies out of the car, your battery can no longer send the 12 volts needed to light the squib and fire the munitions and blow the airbag off. Okay. We need voltage to do that. We need current flow. If the battery's over there on the floor, on the street, blown across the intersection, your airbags wouldn't work, right? So what we do, engineers really, they put capacitors in your airbag module, an SDM or whatever it's going to be, the name of the module. We'll have a bunch of capacitors, enough capacitors to still deploy your airbags for a certain amount of time after the battery's been blown out of the vehicle. Now, why do you care? Well, you might care when you go to work on the airbag system, an SRS problem, and you disconnect the battery and you think the second your battery is disconnected, you're good to go. A lot of times they have you wait a specific amount of time. Sometimes I've seen up to 10 minutes, sometimes 1 minute, sometimes 3 minutes, but sometimes up to 10, where you got to disconnect the battery and then wait a certain amount of time. So that way, you know, the capacitors are discharged, so that you know you can start testing and things like that. So you don't accidentally maybe give a false reading on a sensor, or maybe apply voltage to a deployment circuit and experience the big. You want to say the subwoofer goes boom. Wait till an air blows the cover off of the steering face and all that type of stuff, right? So after the fact, and similar to capacitors used in hybrid and EVs. So you might power a hybrid EV, and there's still the potential and stored in the capacitors enough to make it so you get high voltage. Similar when we're working on these hybrid EVs, it has a time. Disconnect the battery and then wait a certain amount of time. Cool. That's capacitors. And then there's kind of a fun an exercise that you could do. So like if you were to actually put your meter across the capacitor, you can verify whether it's been discharged or not. They can be hard to actually get there. You could also use the meter to measure the resistance between the positive and negative terminals of the capacitor. And then sometimes some meters have the capacitor test function, which can actually give us a number for how much energy the capacitor can store. So that can be like, telling if the capacitor's still good or not, and actually overall like the size of the capacitance. Cool. So some meters have that, some don't. All right, now we're going to jump into electronic components, which is really the part two, but part one got a little excessively long, so we broke it up. That was the finish of part one, which we're going to call part two. That was all electrical components. Now this is electronic. So simply put, what's the difference? Electrical is going to have, electronics are electrical, but electronics specifically tend to be solid state, non-moving. Like a relay, for example, has a click and a movement. That's not electronic. A transistor, as you'll see, will be electronic. It does what a relay does, but using PNP material, semiconductors, and no physical movement. Make sense? So they're a little different. Components starting off with, I'd start with a few of these. And then I'm going to, I actually shot this video earlier, and then I got to stitch them together because I screwed up on the screen share. All right, so let's start with coax cable. Coaxial cable, it's like the same type of cable that you have for your cable TV, which is the thing we had in the old days. It was a black cable. You had to screw it on the back of a cable box or your TV or whatever. Coax. We have coax in the car. It may be like for an antenna or some sort of communication or something, but we do actually have coax. We don't typically repair it. I mean, if the coax is damaged, you're going to replace the whole coax cable. We also have shielded wire. So this symbol's a little hard to see, but it's like a wire, but it shows something kind of going around the wire. That's the shielding. So like a lot of times, the shielding, for example, would be a, a metal around the wire harness, so that if you have electromagnetic induction, like we talked about with motors in the part one, the electromagnetic induction could induce current flow into the wires. Well, we don't want that on some of these important wires, like wires that are going to be maybe wires that send a signal for the rear view camera, for the backup camera, to the actual head unit or to the radio. If we get induction into those wires, that can make the picture fuzzy, right? So we may put a shielded wire in there. They may be double helix, they may be twisted pair, but they may also have a drain wire that's like a casing around them. Sometimes it almost looks like foil, and it goes all the way to ground, and the actual shielding casing will go directly to like a chassis ground. So any current that would be induced into your signal wires, it's not likely, because it's the path of least resistance, and instead it'll go to that shielding, which will drain to ground instantly, right? So that's shielded wire. The junction point is just saying, like, when you look at a wiring diagram, and they vary, you got to know if a wire is crossing over or actually connected. If it's a color wiring diagram and the two wires look like they go together and they're the same color, if they're the same color, those are going to be connected. But on some, it's black and white. If it's a wire and it comes together like this, and it's a dot, and they come together to like a circle, like a dot, like what this is kind of trying to show, those are connected. Sometimes they come together and it almost looks like they go to like a hexagon or like a stop sign. Those are connected. But if the wire comes to another wire and then it does like a little jump over, like a little whoop, those would not be connected. So just make sure when you look at this wiring diagram, you need to know when the wires are connected or not. And they vary from one make to another make, especially when you jump from American, Japanese, and German. They're all different. Okay. And then you guys know ground connection. This one's chassis ground. Sometimes they interchange this ground with this ground. This ground's kind of weird. The M, it's almost like it's biting into the chassis or something. I kind of like this style, but whatever. Connector we'll come back to. Lamp just looks like a bulb. A push button indicating lamp, whatever. NO. So if you look at this connector, or this arrow, it's kind of going up, and there's a connector right here. NO is normally open. So the fact that this is drawn as open, that means it's normally open, which means you have to close it to have it be a complete circuit. So for example, a relay is typically normally open. You have to magnetize the relay to have this contact or touch, and then it's closed. But normally, without the magnetization on the coil side, it's open normally, right? Normally closed is opposite. It's normally closed, and then if we magnetize it, it's open. Or if these were switches, this switch would be normally open, and you have to press it to close it. That's like a horn switch. Or this one would actually be normally closed. Like, for example, sometimes they have switches in the ASE system. A high pressure cutoff switch is for when the pressure is too high. They're normally closed, which allows the compressor to work. But if you get so many PSI, it'll open this up. It'll turn your compressor off and disable your AC because you're over pressurizing, right? So look at it. It's either normally open or normally closed. These are kind of similar, but these are for micro switches. Circuit breaker. This is your relay. This is a relay coil mostly. It could look like this, but it mostly looks like a coil. Here's a transformer. You see the coil of wire not touching the other coil. Maybe this is the primary inducing into the secondary or whatever. A couple fuses. The capacitor, they're interesting because they don't touch. A resistor or another type of resistor, both resistors. Potentiometer, you can see it's like a resistor, but it's got a little sweeper arm. That's a potentiometer. Transistors, I'm going to show you. NPN or PNP, it's hard to tell the difference. A diode, and this diode has a little arrow, and you're going to learn a little bit more about diodes, but this diode, the arrow is kind of pointing like this, Like, let me go ahead and I'll annotate because that one's pretty tiny, and I'd like to show you that. Let me see. Can I get my drawing stuff? Let me check where Zoom is at. I think that would be very good. It's gonna be right here. Let me pull this over here. Okay, that's kind of weird. All right, so if I looked at, oh, this is cool. It's gonna make me draw on screen too. I think this will work. Wow, that's interesting. So I can actually use my touchscreen. Wow, my computer must have just done an update. I've never seen it like this. All right, so if I look at this diode right here, uh, no, I'm gonna have to do it not with my pen. But this diode has a symbol that looks like this. Okay, and then this current flow. This is kind of like an arrow, right? Current flow will go this way. Yes, but it will not go this way. That's a no. Okay, and that's kind of what that diode is showing, right? So if you see a diode, you got to pretty quickly be able to know, like, hey, which way does that flow? Cool. Um, and Zener diodes are similar, but just I'll cover Zener diode later. TAC, motor's a pretty common one. The battery, a switch, that switch happens to be normally open. A relay, kind of normal stuff. Yeah. Okay. Next, let me explain the connector and the chevron. Okay, hold for that.
See a chevron, sometimes what it'll look like is this. It'll look like like a chevron. See, if it looks like that, ugly drawing, a lot of times what it's saying is this is the male connector, the male plastic connector, and this is the female plastic connector. It sounds like dumb, like it's not that important, but actually it's pretty important. And the reason it's so important is because let's say you go to do a test on the wire harness and you want to test the side that has let's say that you want to test up here, right? Let's say you want to test this side. Maybe this side has 12 volts. You'd actually have to find the connector and you're not sure which way it's going. So if you looked at that diagram, you'd be like, oh, okay, if I find the connector and I disconnect it, this is the male side, so you could actually probe the male side. But then if you wanted to test the female side, you'd have to look at the chevron and be like, oh, if I test the female side, that's down here, right? So it's mostly to help you on the car know which side is which. Cool? All right, and then as we jump into electronics, just understand the older cars really had no electronics. You didn't have to know that much about electronics. Unfortunately, or fortunately, depends on how you look at it, the newer vehicles are going to be very, very electronic. And, like you could see even here, straight from the text, kind of silly, but they're more complicated than the actual space shuttles that got us to the moon back in the day, right? Not than the new space shuttles, but than the original ones. It's kind of ridiculous to think about it. We used to just be able to work on, carburetors and engines and pistons and, and any electrical thing would be like maybe the light didn't work and there you could easily see the wires. There's a lot of stuff going on in the modern vehicle. So with that being said, we're going to kind of cross over into what might be seen as like IT and a little bit automotive and a little bit of electrical engineering. And that's all what it really takes to be a current technician. Cool. So some of this stuff is going to be a lot to handle, but you'll be all right. So back in the day, vehicles had no computers. Then they had like at least six, like 6 computers. Anybody have any idea how many computers are in their car right now? Depends on what you drive, of course. I guarantee, yeah, that might be if it's old. But if somebody's got a car that's like 5 years old, it's probably closer to 100. So you know, okay. Now I'll clarify this. Right? Potentially over 100. Each computer could be as complex as like the engine control module, full big computer running all sorts of processes. You don't have 100 of those. But if you go to an old car and you put the window up and down, that was a power window switch, and that was it. It was just a power window switch. We'd send voltage to the switch, and then if you pressed it down, it would send voltage to the window motor. That was it. But see, it gets kind of complicated, because what if you want to have a system where you can control your windows through an app? Or what if you want to control your windows through the remote? Quickly they realize, like, the switch is just the switch. You need somebody to press it. But if you want to be able to have it integrated with other systems, they took the switch out and they put a little computer in instead. So the driver's door module is a computer. Sometimes it's the form of that switch, or sometimes that switch is just an input and there's a computer in the door panel. But I guarantee you on the newer car, there's going to be some sort of a computer for the driver's door. And when you press the window down for the passenger side, you're more telling the driver's door module that you want the passenger window down, which is not going to send voltage directly. It's going to communicate and send a signal to the passenger door module, which is going to say, oh, I just got a message on the CAN network or the whatever generic network that they're requesting that the passenger window go down. Yes or no? Okay, put it down, right? So back in the day, your master switch literally sent the power to the windows that you wanted down. Now, no, your master window switch sees your request, sends it out on a network, and the other computers see it, and they're like, put it down or don't put it down. Make sense? So it's not that we have a billion ECMs, it's that simple things that used to just be switches are now modules. In addition to, now we got an engine control module, a transmission control module, typically an ABS control module. If it's got electronic power steering, that's an electronic power steering control module. If you got a vehicle with a really cool rear differential that does like torque vectoring, it's got a differential control module. You got four-wheel drive, it's probably got a four-wheel drive control module. And then if you've got, let's say, keyless entry control module. We talked about the power door modules. A lot of times your fuse box will be like a power distribution module or something along that area. If you have a rear fuse box, it might be like the rear area module. All of your lightings are controlled by a body control module. Cool. So let's say you went back in the day and it was a 71 Chevelle and the taillight didn't work. You'd be like, oh, the taillight doesn't work. Let me turn the lights on. Let me go back there and check for 12 volts and check for ground. Or better yet, honestly, you'd unscrew the two screws. You'd pop the bulb out. You'd hold it up to the light and be like, oh, yeah, the filament's blown. Let me get one. Okay, it's fixed, right? Now, no. The Chevelles are gone. That's the only reason it's different. So now rather than a Chevelle, let's make it I don't know, you pick. What are we working on? Something new. New as in like 5 years or less old. Pick something. Come on. Anything? Nothing? Okay, yeah, we can go with that. A Kia Sorento. Times have changed. All right, if I'm going to say those are most likely LED taillights, so we're going to go like that. You go to look at the Kia Sorento, the left side taillight doesn't work. You want to take the bulb out, there is no bulb. It's an LED, there's nothing to see. You have no idea if the LED is good or bad. I mean, it can be just as simple as checking for 12 volts in ground, that's true. And if it has 12 volts in ground, it doesn't work, it's no good, boom. You're going to have to unfortunately sell a $500 taillight because it's got the whole LED printed circuit board and all that. But maybe eBay's got some kind of a deal, or maybe the Yonke yard or something. But let's just say it doesn't have 12 volts though. On the Chevelle, we sent 12 volts to the light switch. You turn the light switch on and it passed the 12 volts back to the bulbs. If it doesn't have 12 volts on that Sorento, you got to look at the diagram, okay? So I'm going to improvise what I approximately how it'll work. The 12 volts for that tail light will almost guaranteed be coming from the body control module. So you might have to trace up to the body control module. If you have an open in the wire between the body control module and that tail light, it's actually not that different than the Chevelle to diagnose, except you can't see the filament because it's an LED. But checking 12 volts in ground, that's about the same. But let's just say you go to the body control module and the body control module is not putting out voltage. And you're like, well, first off, it's probably the body control module, but I don't know that we can quite jump to that conclusion, and mainly because of the cost of the BCM. But I'll tell you a pretty fun example of what burned me, and it, matter of fact, was a Kia Sorento, but it was years ago. So it'd be like a 2012 Kia Sorento. I had one that came in. The taillight was an op. I pulled it in. I'm trying to be quick, right? Flat radio style. Pulled it in. Taillight was blown. I saw it wasn't working. I pop it apart. I pull the bulb out. The bulb is blown. I can see the filament it's no longer connected. There's no reason for me to get out my meter and test things, right? I can see the bulb. I take the bulb out. I put the new bulb in. It still does not work. And I'm like, no. Then I'm kind of like, that's weird. Like, what are the chances? The bulb was absolutely bad. So it had a bad bulb, but it also has another problem, apparently. Would you agree? So I'm like, all right, whatever. Now, mind you, I'm gonna just say, this detail seems like it doesn't matter, but it does. I pulled the car in. I think I did turn it off, but then I turned the key back on, push button, click, click. I left the key on, pulled the bulb out, put the new bulb in. I noticed something too. When I checked the bulb, the filament wasn't like just blown apart. Actually, it was kind of like falling down, like mixed into where the base of the filament comes in. And I was like, oh, okay. I put the new bulb in, it didn't work. So then I get the wiring diagram. I have to start checking. There's no 12 volts going to the bulb. So is that kind of weird? Then I go up, I get my way up. There's a body control module. I check coming out of the body control module. There's no 12 volts. Doesn't that tell you the body control module must be bad inside? The body control module is supposed to give the voltage. It's not giving the voltage. Part of the reason I say, like, sometimes recheck and think before you sell a computer or things like this. It doesn't work. The BCM is in op. I'm kind of like, what do I do? It could be a BCM or whatever. Just for no real good reason at all. I turn the car off and I start doing something else because I'm just like, that car can't need a BCM and have a bad blown bulb. I go back over to the car, I start it up, and the taillight works. What happened? I'm like, I don't understand. How can this be? It's a good guess. I'll clarify it. A lot of times because remember, we're in electronics now, so we're talking about computerized. I want you to keep in mind, the engineers don't always tell us exactly what they're doing. So what happened in this case, the bulb blew, the filament fell down, it actually caused a short. So on some of these modules, rather than have a fuse for the taillight, they'll actually monitor the current flow. And if there's excessive current flow, they'll just open up the transistor and stop sending current. So I took out the bulb was the short. I put in the new bulb, it's no longer shorted. Why didn't it turn on? I had the key on the whole time. It never really rechecked. It saw the short, it opened up the transistor. I put the new bulb in, but it never really tried to close the transistor and recheck it until I got frustrated, turned the key off, walked away, came back over, turned the key back on, and it's like, all right, let's try that taillight again. Oh, it's fixed. Cool, now it worked. I was ready to sell this customer a body control module. It had been $1,000, right? So the way that we have to diagnose stuff now is just so different than how it used to be. Makes sense? Anytime that the computer's in the mix, which is all the time now, you just got to understand there's stuff that could be happening in there that may not be exactly as it seems. Makes sense? So in this case, it wasn't sending voltage, which would mean the transistor is bad, but the transistor wasn't bad. It wasn't sending voltage because it was trying to protect itself. And until I reset it, it acted bad, kind of in a way, right? Now, interestingly enough, if I were to have put a BCM in there, it would have fixed it simply because I would have disconnected it. It would have powered it down. I would have put the new one in and been like, yeah, I diagnosed it right. But actually, I would have been wrong. So fun, true story. Anytime diagnosing true electronics is going to be more complex because you got within that ECM all sorts of little small parts, and we don't necessarily always know exactly what's in there. Even me with the background of a manufacturer certified factory technician at the factory training center, talking with the factory trainers and all the OEM people. And like I told you that story in I think like week 1 or 2, where I talked with as high up as I would go in service, they're called an STS. They deliver the factory class and certify the technicians, which meant they had to certify me so I could certify the technicians. And I asked him, hey, why don't they show us what's in there? And he said, I've actually asked that already. And remember what the engineer said? You don't need to know. And that was it, right? So we don't, even as high up as any of us will ever make it as technicians. Now, if you become electrical engineers, you may know. But that's not really what this class is, so we're going to do it from a technician perspective. We don't always know the details of what's going on in there. I saw nothing in the service manual about how it will stop sending current to the tail light if it senses a short until it's reset. I still can't find anything. It just happens to be that I turn the key off, just frustrated, and turn it back on, and it's the only thing that makes sense. And I have read about smart modules that can, in a way, like replace a fuse because they can monitor it and open the circuit rather than having a fuse blow, right? So let's define what electronic is. No moving parts, like a diode, a transistor, an integrated circuit. So if we were to look at, let's just say, this integrated circuit, that can open and close circuits, that could send voltage or not send voltage. In a way, it could do some limited processing. So let's just say if you had automatic headlights, how about that? Automatic headlights, when do they turn on? Got to have the switch in auto. What else? Got to be kind of dark outside. If it's daytime, they're not going to turn on, right? There may be a few other inputs, but let's just focus on those two. Got to have the switch in auto. Got to be dark enough. Then it will send the power to the relay to turn on the headlights. Cool? In that integrated circuit chip, it can have a bunch of terminals. Maybe one of these is the ambient light sensor that tells you if it's light or dark, okay? Maybe another one of these is the headlight position. Is it in auto or not, right? Then maybe one of these down here is the circuit that's going to send the voltage to the relay to turn them on, right? So that's what a chip does. That's essentially what a computer does in a small scale. It can have multiple different inputs. It can essentially look at things. Is it dark outside? Is the headlight switch in auto? If yes, then send power over here, right? But the way it does it is it has dedicated circuits. This circuit was for the ambient light sensor. This circuit was for the headlight position. And then this circuit was to give power to the relay, right? That's all about what electronics is. Kind of makes sense? When it's doing that, there's nothing opening and closing. It's just going to be those transistors from before, right? If we want to send voltage on that circuit, the transistor's just going to get a little negative to connect the transistor through and actually send voltage through. If you guys remember the base connects the collector to the emitter. Cool. So we'll get back into transistors, but just as an overall understand, back in the day, there had to be a turn of a switch and a click and a contactor like this to a contactor like this. That's electrical. Electronics, nothing moves. It does the same type of thing, but that's solid state. Okay, so when you hear the term solid state, there's no moving in here. It's a solid state. Chemically, we can we can have it be an insulator or a conductor, depending on what we do at the base if it's a transistor. Makes sense? But nothing moves. Kind of weird, huh? But we need to be able to diagnose those. And of course, they have particular functions. We put them in a circuit to do a job. Like, for example, we may have that, let's say we have that variable resistor. But that variable resistor we may mount to an arm that's a fuel float for the level sensor, right? But it's still, that sensor itself is electronic. Okay? And then a lot of times what we'll do is we'll put them on circuit boards. Like all these, rather than these being very complex and in the wire and this one and this one and this one, we run the wire into a circuit board. We print with, you know, picture a 3D printer, except it's printing with metal. We'll print a little circuit to this thing, and then we'll solder a little resistor, and then we'll print a circuit over to that thing, and then we may put an LED in. Then we can print a circuit over here and have it go to a transistor. We could print a circuit over here and have it go to a integrated chip or something. So we're going to take the circuit board, and we're going to have all the components we need with little printed circuits going everywhere they need to go. So it's a very, 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 very complex circuit, but it's tiny because it's printed up on a little chip with a bunch of little components soldered in. However, you still need to understand it. You still have to be able to test those components to determine, is it in the computer, is it in the module, or is it in the actual wires? We can repair the wires, but we don't go in the module and repair the printed circuits. Now, someone could, I admit. And I've even seen some techs start to dabble a little bit in that. It's pretty interesting. But generically, especially as I'm held to the standard of ASE, that's not what we do. We don't do that. We do it way different. Okay? Cool. So if you can just consider that, that's as far as we really need to go, but we still need to be able to diagnose it. Like, for example, if it's a diode, we can test diodes. There's a diode function. Remember, that's kind of like a one-way check valve. So we could use our meter to do a diode test, and we could actually test a diode that's inside of a computer. We just aren't going to break it open and solder a new one in. We'll be like, yeah, it's got a bad diode in the ECM. It's the ECM, period. Cool. So like if we look at a diode in an image, you can see this. What's kind of interesting. This diode has an N, a depletion zone, and a P. And if you look, this one actually is a reverse bias. So if we try to send a positive here, it can't go through. It can't go N depletion P. What it can do, this would actually be able to go P depletion N. So how could we get current to flow on this diode? We would actually have to flip it. So if we had a diode and it was in there backwards, it wouldn't allow current flow. We could actually flip it to allow current flow. That would just be an installation error. And actually, let me look at that for a quick second. P to N. Actually, a reverse bias will go N to P. I believe that's correct. But let's just say that we were to focus on a forward bias diode. We have P and N. That's going to actually allow, it depends on if we're doing conventional or electron theory, but let's say we're doing conventional. If we try to have current flow out of the positive and go P and then N, it won't flow. So if we were to flip it and have it go positive coming out and go N to P, it would flow. Kind of makes sense? We don't really flip the diodes though. What we'd be more likely to do is, like we talked about a little bit before, if we think there might be some sort of an electrical kickback, like a spike, like if we have a relay that's opening and closing, or even better yet, a compressor clutch that's opening and closing, when the compressor clutch is connected and then it's open, sometimes it'll get some electromagnetic induction, and it'll actually make a voltage spike to go back to the ECM. We'll put a diode right there. And if we put a diode right there, and let's say we have the diode in this direction, positive can flow through here, but then when we turn the compressor clutch off and we have a little voltage spike here and it tries to go backwards, it won't let it, right? So the diode just makes it so we don't get that electrical kickback. That's most of the time what we're going to use it for. Sometimes if you were to experience, I don't know, maybe some version of a circuit where you wanted a, you saw where a diode would benefit you. They may use a diode just to make sure electricity doesn't flow this way, but it flows that way or something, right? So anywhere that they deem a one-way valve would be helpful, that's where you could see a diode, okay? A one-way gate's a good way to put it, a one-way gate. But again, that gets a little bit more into the electrical engineering side for us. Like, we don't determine where there should be a diode, but if there is a diode, we would be able to test the diode. Partially with this that throws me off a little bit is normally I look at a diode and it has a symbol, and I'm struggling to remember reverse bias. I believe this will not allow N to P, and because we're trying to do N to P, the depletion zone is going to expand and no electrons will make it through the depletion zone. Whereas if we flipped it and we try to do P to N, I believe it would go through. But that part I'm a little bit fuzzy on. What I would know is if we were to go over here, and like as a technician, what we do is we're going to bring this bad boy over just a little. If we were to do a symbol like this, and let's say it would look like this, that tells me it will not flow this way, right? Because you can see how the arrow goes the other way, but it would flow this way. Cool. So all we would really need to do is look at that diode symbol. I just don't remember which one is the N and the P and the N. I don't recall. But what I would do is I would take my meter, and if it's supposed to go this way, I put my positive lead here, I put my negative lead over here, and I put it on diode test, and should it flow this way? Right? If you look at the arrow, doesn't it look like it should flow right from right to left? It should flow. Cool? But then I would put my red lead over here and my black lead over here, and it should not flow. That's it. You just put it on diode test, make sure it goes one way, but not the other way. Sometimes a diode will flow both ways, and that would be a shorted diode. So you see how it goes both ways? That's a short. That's no good. Other times it won't flow either direction, and that would be an open diode. They fail both ways, but it's an easy thing to test with the diode tester. It's not a real big deal. In fact, I'll have you guys do a diode test when we do the electrical boards. No big deal. All right, cool. And then I think this actually is probably what I would have needed to brush up on, but a forward-based diode will conduct current and allows a small amount of voltage to drop across, leaving the remaining voltage free. So yes, a diode does consume some voltage. It's a one-way gate, but it consumes a little bit because it takes something to function, right? And then of course if the polarity gets reversed, all of it will drop across the diode, no current flow. So if it's in the right direction, it drops a little bit of voltage, but a lot of voltage makes it through. If it's in the wrong direction, or in the case that they put a diode in to block that voltage spike, none of the voltage will make it back to the ECU. It'll all be dropped, no current flow, on purpose. Okay, there we go. The P commonly on the positive side is the anode, and the N positive on the negative side is the cathode. That's actually what I was missing in my mind. So this will not flow because look, N, you've got the positive trying to go to the N side, that's a no. And you got the P side trying to go to the negative, that's a no. So this is a no flow, whereas if we flip it positive to the positive side, to the P side, negative to the N side, that will flow. So if you got the positive with the anode and the negative with the cathode, that's a yes. But again, I'm going to give myself a little bit of leniency because you're never going to see a diode labeled the P side and the N side. You're going to see the symbol. You absolutely have to understand the symbol. If you kind of forget the P versus the N, welcome to my club. Cool. So here's an example of what the diode would look like. It's very hard for you to see the symbol, but there it is. If we were to throw the diode up here like this, if you look, now you've got the positive, the P side with the negative, that's backwards. So if you were to try to send current out the positive, go through the bulb, you got the positive side going to the N, that's the cathode, that's blocked. If there's no current flow, what's up with the bulb? Yeah, no bulb, no current flow, no bulb glow. But then if we flip it, we've got the positive going to the actual P side and the negative going to the N side. That will actually allow the flow and the bulb will work. Cool? So it's just a one-way valve. That's it. No big deal. Of course, it has to be installed correctly. All right, but wait, there's more. There's your diode symbol, okay? So if your diode symbol is this way, the current can flow from right to left. It cannot flow from left to right. It would block it, okay? But what if we had a light emitting diode? Well, that's an LED. So if the current tries to flow from left to right, you get nothing. But if the current flows from right to left because the arrow points left, not only will it allow the current flow, do you know what also happens? The LED lights up. It's kind of interesting. Back in the day, we just had the big filaments in the bulbs, but now we have diodes that will emit light if it's flowing the right way. Cool. So mostly we're using LEDs for the light purpose now, but technically you could use an LED as a diode. You just would get light as a side benefit. And then a Zener diode is different. So as it shows, it can allow current flow in one direction, but only up to a specific voltage, okay? So let's just say we put a Zener diode in the automotive system, and we were worried about generating too much voltage, and we never wanted to see over 14 volts. We could essentially put a Zener diode in that's a 14 volt cutoff Zener diode, and if we're flowing 12 volts or 13 volts, it's going. But what if it tries to flow 14.1? It would block it. Make sense? That's why they're calling it a voltage regulator. It regulates the voltage so it doesn't make too much and damage stuff. Cool. So we will actually use those in in an alternator with a voltage regulator. We use a bunch of Zener diodes. Cool. Different symbol. Notice that? And now look at the photodiode compared to the LED. What's different? These arrows are going out, so this emits light. This diode changes its conductivity depending on how much light it sees, right? So we've got current trying to flow this way. Depending on how much light is coming in, it'll allow more or less. That's very interesting. An LED makes light, and this measures light. Why would we want to measure light? Who remembers the talk about the automatic headlights? Yeah, if you have automatic headlights, that's what we're going to add. We'll add a photodiode, and the photodiode will determine whether or not it's light or dark outside as an input to the computer, and then the computer will be like, oh, it's dark out, turn the lights on. Or it's light out, don't turn the lights on, right? So it's a sensor is all it is. How do you think you could test it though? Right, if you test an LED, you give it 12 volts and ground and the light would light up, right? How would you test a photodiode? Tell you, you can actually measure the voltage coming out, right? The voltage going in stays the same. The voltage coming out is going to vary depending on how much light it sees. So you try to measure the voltage coming out with it dark, and then you'd shine a flashlight on that sucker, and this information's hard to find. you would shine an incandescent flashlight, not an LED, but like an old style bulb, like not even these are fluorescent, but you know, like your typical screw in type of bulb on an old work light would actually allow more voltage to pass through the photodiode. That's how you test it. How I would honestly test it though, I'd get the scan tool, I'd go under the ambient light sensor, which is just another, it's the name of the sensor that uses the photodiode. I'd cover it up. I'd see what the reading was. Sometimes it measures it in volts and other times it measures it like in lumens. And I'd go park outside. I'd cover it up and it should be low, and then I'd take my hand off and it should be high. You know, I would test it with the scan tool looking at live data, but if you had to test it removed with your meter, you'd measure the amount of voltage that's passing through, depending, and it should be proportional to the amount of light hitting the sensor. Cool. And so, I mean, basically, that's kind of the gist of diodes, right? You could get really into, you know, the P and the N and the junction, and depends on exactly what happens. But, you know, in summary, this diode is installed backwards, and you notice this depletion zone. It's essentially like an air gap. That's kind of what this is explaining. It's got a hole. So if you have the current trying to flow the wrong way, it'll create a hole which will make it an open. It'll be open. Cool? Because it enlarges the depletion layer, which makes the insulated space larger, which will stop the current flow. That's another way to consider a diode. So if you have it backwards, it tries to flow the wrong way, this will open up as a depletion layer, like a hole. Cool? And won't flow. If you have it the right way, the hole closes up, and now you can actually have a current flow because the N will conduct to the P. Cool, little shake. Yeah, definitely bouncing the screen. All right, so if it gets bad, we'll run. And anybody's free to just jump out that exit door, but I think we're good, okay? By the way, this concept is going to carry on into capacitors as well. So here's how we actually test it. We're trying to test the diode reverse, and it's OL. We flip the diode, and we try to test it correctly, and now it's just dropping like a half a volt. Cool? That's it. This diode test passed. It's that easy. Cool? And then LEDs, like we talked about. Remember, LEDs have a resistor because we need to drop that voltage down. The LED having a resistor has a bit of a benefit as well. We have very low current flow required to run an LED, so they're more efficient, right? So if you have LED lights in a home, you're going to use less electricity for the same amount of light. If you have LEDs in a car, think of why that's going to be preferred by the government for emissions and fuel economy. Why? It has to do with this. If we go to LEDs, it requires less current, which means this alternator doesn't have to make as much, which means we can save a little bit of gas and we can lower our emissions slightly. So the trend is going to be going to LEDs. LEDs look cool, but the real reason that we're pushing LEDs, fuel economy and emissions. I'm going to say that 1,000 times if you keep taking classes with me. If you understand, that's the push, right? The government goes to the manufacturer and says, hey, average vehicles by 2030 need to have 50 miles per gallon for cars and 35 miles per gallon per trucks. And they're like, how? And the government's like, I don't know. You're the manufacturer. I'm just letting you know. We came up with these numbers. Make it happen. Don't call me. I don't know. Bye. And so then the manufacturer's like, man, how are we going to do this? Well, a lot of things. Engines are smaller, but they might add turbochargers. And engines are typically, you know, low tension rings and maybe suffering from oil consumption and all bad things. And people are mad at the manufacturer. But I look at it and I'm like, I'm pretty sure, honestly, Generous Motors, you know them? Generous Motors would probably still be putting small block Chevys in their cars because they had that thing dialed and they were making it. They were making it cheap. And then why you think they reinvented it? It's not because they were bored. It's because they government rolled up and it's like, hey, that thing doesn't get good enough emissions and the gas mileage is bad. You need to get rid of that small block Chevy. Small block Chevy is going to go away, right? So same with LEDs. Now, I like LEDs. I like the light. I like the white light better. I like the little patterns. I like all that type of stuff. Depending on what vehicle, I'm even potentially willing to pay for that. But just so you all know, it makes your job harder because to diagnose this, you can't look at the filament anymore. You got to actually check it for 12 volts and ground and stuff. And then you can't replace one of these. You're going to replace this whole thing, this whole thing, this whole thing, right? So understand. I may regret this, but I'm going to tell you how I really think. People aren't that smart, right? They buy a car, it looks cool, they like it, it's also been designed with government standards in mind. Then the car breaks, the taillight doesn't work. They bring it to you, you're like, I don't know if it's a taillight bulb or like there's no taillight bulb. It could be the taillight, it could be the wiring, it could be the module. I got to charge you to diagnose it. And they're like, these crooked, unethical mechanics are just ripping us off. I'm sort of like, I would have worked on the 71 Chevelle. I don't care. But why can't I work on that? Mainly because the government said fuel economy and emissions. So instead they roll, and safety too. Safety's a big one, right? So when they roll out this fuel economy and emissions and safety, we're no longer working on the 71 Chevelle, we're working on this. I mean, everybody goes to work and they want to get paid, right? We're not going to be any different. So I have no interest in billing people diagnosis money if I don't need to diagnose it. Diagnosing, it's like, there's plenty of work out there. I don't need to make diagnosis when there's no diagnosis. But the truth is, if this doesn't work, I don't know what's wrong. I need to check it. I need to measure some stuff. I need to determine why it doesn't work. It's not ethical to say, hey, let's throw in a $700 headlight to see if that fixes the LED problem. And if it doesn't, then I'll charge you more money to actually diagnose it. Like, you got to do the diagnosis up front. That's the trend of the industry, right? But like I said, people aren't that smart. They're mad because they're paying money for diagnosis and they're not even exactly sure whose fault it is. But you're going to get blamed. I'm going to let you know right now. They're going to be like, why are you taking my money? And be like, I mean, when you go to work, why are you taking your company's money? Like, it's the same. So if we're going to diagnose the car, we got to get paid. Otherwise, you could do diagnosis all day long, and then they'll take their cars to Mo, and Mo will fix them cheaper. Remember? That's what Mo does. Cool. So this rollout is more than just they look cool. And some of it may be that they look cool, right? Like if somebody's got, you know, they got a little more money and they're trying to impress somebody, they may buy it because it has the cool LED designs. That's true. But you're seeing LEDs on the more basic vehicles because of fuel economy and emissions. So making it more difficult, okay? It just is. Get used to it. You are going to take the heat for that. Cool. Zener diodes, I think we're probably pretty good on. The LEDs are more fun because it's a diode that puts light out. The Zener diodes, like we talked about, voltage regulator stuff. If we were to combine a bunch of these Zener diodes, we could actually make it into what's called a rectifier bridge. In fact, the rectifier bridge could use regular diodes, but then we could also combine Zener diodes to have it be a rectifier and regulator. So a rectifier does kind of like what it sounds like. You're going to erect the building. You're going to stand the voltage up. So if you had, remember we talked a little bit about AC voltage? It goes ups and downs, right? It's positive. It sweeps to negative. It sweeps to positive. That's alternating current. Just imagine for a second, like if we look at this rectifier bridge, if you were to look at this has 3 diodes. Imagine the 3 phase of AC. This one's up and down, up and down. This one's up and down, up and down. This one's up and down, up and down. Imagine what a diode does. When it's going up, it's allowing the flow. When it tries to go negative, it blocks the flow. Cool? And then same with, that's the X, the phase one, we'll call it. Then phase two, it allows the up, but it blocks the negative. Phase three, it blocks the up, but it allows the up, but it blocks the negative. You could essentially eliminate all the negative. If all you have is the positive and the negative's gone, it's no longer AC. It's now DC. That crazy or what? So you have AC positive and negative, but you hack off all the negative because the diode won't let the current flow the wrong direction, right? That's a way to skim it to become only DC. So we'll take 3 diodes typically, attach it to the 3 phases of AC, and this will rectify it into DC. And this is built into the alternator, so you know, on a new one. So everybody knows now, because we're going to cover alternators in detail. Okay, so this is just an electronics concept. When I spin this, initially it's making AC voltage. Remember how that conductor gets closer to the magnet, and that's getting up and up and up, and then as it gets further, it comes down, 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 and then it gets closer to the next one, it's up and up and up. This is making AC. We don't want alternating current. We want DC. So the AC current goes into a rectifier bridge, which cuts off all the negative because the diodes won't let it flow reverse. And that puts out DC now. However, if you're going down the highway at a legal speed in 6,000 RPMs, you're going to be making a lot of electricity. We also will use Zener diodes to make sure we don't exceed, let's say, 14.1 volts or whatever the number is. That's going to be the actual voltage regulator side. So we need to rectify it from AC into DC, and then we need to regulate it to make sure that we don't make like 15 volts. That's a regulator and rectifier. On some, like on motorcycles, those tend to be separate. You can have a bad regulator and rectifier. But on alternators, you technically could have a bad voltage regulator and or rectifier. That's all this stuff in the backside. But if you go buy an alternator, guess what? It comes with all this stuff. So you're kind of like, I don't really care if it's the regulator, the rectifier, some with the winding, whatever. It's getting a new alternator. Boom, put it on there. Somebody else will remanufacture it, but not here. Cool. And that's kind of like the crown jewel of understanding diodes. Cool. Diodes, we can make AC into DC, and we can also regulate the voltage with Zener. Cool. All right, now, and I'm mostly going to try to hit the really important parts, but now we're going to discuss, if you knew, it's the second time you've seen this. Remember I told you typically you need to hear this a few times to get it, but if you knew how to diagnose this thing from last week and the week before, I'm going to get you where you could diagnose this thing. All right, let's start off with this. What is this blue-gray thing? The relay, right? What's the load in this circuit? The motor is the real thing we're trying to control. And the truth is, the computer isn't good at controlling this stuff. This is all high current. So if we wanted to control it with a computer, we would do it here, right? If we gave 5 volts from the computer to the coil side of the relay, that would actually close the relay, and then current would flow 12 volts through the motor into ground, okay? Hopefully that's starting to make a little bit of sense by now. In fact, if I'm going to be thorough, let me go ahead and I'll do my drawing. Oops. I think I went a little too far. All right, because the transistors it's something that we're going to see every day, okay? So we want 12 volt. It's interesting because this is a ground side. I should actually highlight that. This is a ground side control, which is fine. So we should have 12 volts go to the motor, and then we should have ground leave the motor, but the problem is ground starts here and goes up and goes here. Oh, look, because we have 5 volts and this is magnetized, it's closed. So now we should have ground going here, correct? But that's only because we sent the voltage on the coil side right there. The second that this gets 12 volts and ground, it's magnetized, it pulls this contactor over. We agree? So if that's the case, how do we actually control it? Well, we give this or we take it away. So if right now there's nothing here, there's no ground to the motor's off. Am I right? So what do? I give 12 volts. That magnetizes this coil. When it magnetizes that coil, which is normally, that relay switch is normally open, the second I magnetize it, it will be closed like it is. I actually need the green one. It's ground side. Then the ground will make it up to the motor. Now what's the motor? It's not off anymore, is it? It's on. All right, if we're going to apply that to a transistor, are you ready? We've got ground here. What we also have is we've got positive right here, and that's it. How would the transistor turn on the motor? Bingo. If we apply 5 volts to the base, that will connect. This is going to be an NPN. That would actually make it so that the ground, it would do the same thing as the relay. The ground will basically come through this way, or in a way you could think of it the other way. It'll allow current flow like this. Now what's the status of that motor? That's it. It's almost the same, right? Like over here, we apply 5 volts to the coil side of the relay. Over here, we apply 5 volts to the base of the transistor. Who cares? It's the same. It's not. This is not really anything that different, right? Some would even say the transistor is like a solid state relay, because the computer will mostly control this little 5 volt base, whereas the computer used to control the 5 volt little coil side. And these could be 5 volts or they could be 12 volts. It doesn't matter, but they're very, very low current. It's going to be like a tiny printed circuit, a tiny little wire. A tiny little wire that's going to control a big wire to run the motor. Make sense? It's the same. What do you think the positive is of a transistor, though? There is a positive. I guess maybe to help you, what could go wrong with this relay?
It's more reliable.
It is more reliable, but why?
Less moving parts.
Moving parts could be problematic. There are no moving parts. It's solid state. Nothing moves. It's an isolator, it's an insulator, or it's a conductor. It isolates or it conducts. That's it. So if you think about it, this relay clicking and clicking and clicking and arcing, but eventually this little contactor could be burned or messed up or corroded or whatever. Some stuff could go down. But in this thing, this transistor, these are pretty reliable. And this is the essence of electrical versus electronics. When it's electronics, we can turn stuff on and off, but there's no clicking, there's no moving, there's no stuff, there's none of there's no movement. There's just conductor or insulator, right? So this should give you a really good understanding of the why and the context, but we have to actually look at how it works, though. So keep this in mind. And then here we've got an NPN. Here we've got a PNP. It's just negative, positive, negative, basically. The collector is the in, the base is the controller, and the E is the emitter. That's the out. Now, normally we picture this being on the positive side where 12 volts comes in to the P. We're going to control the N, and then 12 volts goes out with the E, but this would be on the positive side of the circuit. You saw on this previous page, we actually did it on the ground side. You could put it on the ground side. You can have the transistor give ground or not give ground. It's just a lot of the times the transistor gives power or doesn't give power. But it doesn't matter. They work the same. So if you think about it, if we have power coming in on the P, we actually have to give typically ground to the base, and that will allow the power to flow throughout the other P, which is the emitter. There's no moving parts. There's just molecules, just kind of like the diode. Remember the hole? So if you have no negative coming onto the base, this becomes a hole, and the P is air gapped away from the other P. There's no flow. But if you give the base negative, then all of a sudden the P conducts to the negative, which conducts to the P, and now there's flow. Cool? So it's a solid state relay. It's basically what it is. No moving parts. In theory, at least know where. You could also consider it's an electronic switch. The only reason I wouldn't say it's an electronic switch is we're using small current to control large current, so I really think of it more as a solid state relay, but either way, it's okay if you think of it like that, because it's all inside the ECM. If you think like, oh, for an injector, the injector needs to get pulses, right? Remember we saw that last week with the test light. Remember we saw the flash. The ECM needs to pulse the injector. Let's say it's pulsing the ground, as many do. If we need to pulse the ground, how can we do that? We could use a transistor. The transistor will give ground, don't give ground, give ground, don't give ground. What if you were to roll up to the injector and check the pulse and find the ECM isn't pulsing the injector? Then you could back up and see if the ECM right at the output connector of the ECM, is the ECM pulsing at all? No. Then you'd be like, oh, it's got a bad transistor. We may call that a bad driver. You'd be like, oh, it's got a bad injector driver. How do you know? Because I went right up to where the emitter would be at the outside of the ECM and I checked it and there was no pulsing. It should have pulsing. Right at that point, though, like just based on my experience, like the one with that Sorrento, I might make sure there's no codes, like just do a little bit of thorough investigation to make sure that there's not a reason why the ECM is not providing the pulse. Like, for example, how that filament shorted and made it so that the ECM wouldn't provide the pulse, the power to the bulb, right? But basically, we're there. That's how you do the diagnosis. Uh-huh. From last week. Exactly. Right? Not just on or off, but on, off, on, off, right? That's a pulse. So the injectors, for example, get a pulse. They have to get a pulse that's so fast. This is perfect. Imagine that relay trying to be like, bam, 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 bam. That's going to be like, the relay's going to be like, I'm done, I'm out. So the transistor's perfect. These can be cycled on and off extremely fast. There's no true moving parts. It's a beautiful thing. But if you were to zoom out on like the context of how I started the class, if the car comes in with a misfire and you think it's an injector, you want to be able to test. Is it the injector? Is it the wiring? Is it the module? If it's the injector, great. If it's the wiring, okay. If it's the module, you're like, oh, that's expensive. Are you sure? You know, if somebody tells me, oh, it's got a bad ECU, I'm like, are you sure? How'd you diagnose that? And if they tell me, I checked the output right at the driver, at the transistor, and the transistor is not providing a pulse to the injector, I'm going to be like, did you check it down at the injector, or did you check it right at the output of the ECM? And if they tell me right at the output of the ECM, I'm like, all right, yeah, go with it. That's the diagnosis. I'm always, even after 1,000 cars, I'm still always a little bit like, I don't know, it just seems weird, but like the diagnosis already confirmed it's going to be the ECM. See what I'm saying? Kind of funny. That's what we do. Cool. And so this is just the words of, how it actually works. It talks a lot about that depletion layer. And so I think I got a picture of that I can show you. Well, the field effect's similar, but just a little bit different. I think the best way is if I show you that back on diode. Remember how way back here on diodes, it would build up this depletion zone. They call that the hole. The transistor does the same type of thing, right? If it doesn't have the correct voltage applied to the base, it'll make a hole, a depletion zone. That's essentially what we're trying to drive home there, right? If there's a small current on the base, it lets the larger current flow at what they call the collector or emitter junction. So if we look at this is the collector and the emitter. They actually come together. If you have the correct current flow at the base, the collector and the emitter are now connected. Cool, that's really what it's saying. Right, and it mentions the depletion layer. So overall, it's not a real big deal. You should know the transistor operates as a low resistance conductor. So when we have the correct voltage on the base, the transistor should have almost no resistance. So it's not getting in the way. It's not consuming much. It's not really a load. It's basically like a solid state switch, a solid state relay. It's not the load. Make sense? It's going to let the current flow very easily through. Cool. And then this is all it's just saying. PNP and NPN, don't be confused. It's whether the base is activated by positive current flow or negative. That's all. So if you want to control it via negative on the base, it's a PNP. If you want to control it on positive on the base, it's an NPN. Now, generally what we would do is we'd probably put the PNP on the positive side so we can have positive in controlled with negative and have positive out. But if you want to put on the ground side, you'd have a negative in, positive would control the base, and a negative out, right? So that first one we saw, this one being on the ground side, this would be an N, a P, note it's a positive control, and an N, negative out. Not a big deal. We could have easily moved it up here and had it be a P in, negative would control, the ECM would control the negative pulse, and then it'd be P out. Not a big deal. Cool. Oh, and FYI, this is a term you must know. High side driver. Do you see that? High side driver. That's when the transistor is providing the positive. Low side driver. That's when the transistor is providing the ground. Which one is this? Bingo, that's a low side driver. That's correct. If we moved it up here, that would be a high side. So sometimes in automotive, we're kind of funny. I'm guilty of this. I'd like to just call it a transistor, but sometimes the service manual will call it like a low side driver, and then next thing you know, all the techs are calling it a low side driver. So if somebody's saying a low side driver, I'm not going to correct them because it's correct. It's fine. It's good. It's legit. But sometimes we try to sound smarter than we are, and I don't really know all the reasons of why we do that, but sometimes automotive people can be a bit, shall I say, prickly. Sort of like, they're not going to be like warm and inviting and be like, hey, it's a bad high side driver, but you know what? I'm sure you took automotive classes. It's really just a transistor that happens to be, it's a high side driver, so it's probably a PNP. They're not going to tell you all that. They're just going to be like, oh, it's a high side driver. It's a low side driver. And you're like, is that something different? No, I'm just letting you know it's the same thing. It's the same thing. It's just a different way to say it. Cool. But some of that, for your record, may be if you go to diagnose this vehicle and you don't write up your story, your technician's story well, and you say, the vehicle had a misfire, went to check the injector pulse, and found it had an open transistor in the ECU. It sounds like if you really think about those words, it sounds like similar to if the computer didn't work and you're like, oh, the customer said the computer didn't work. I looked at it and then I found it wasn't plugged into the outlet. It sounds like it took you no time and people don't want to pay because it doesn't sound like you did that much. So sometimes what we do as technicians is we'll make it a little bit more technical than we need to, okay? And it's kind of dumb, but then again, maybe it's not, because if I say, verified a misfire, inspected the fuel injector, found the fuel injector was not getting a ground pulse from a low side driver in the ECU, further inspected the harness, okay, tested the output at the ECU using my meter and in a low side driver and found ground is not being conducted through the transistor, then be like, oh, take my money. I don't even know what you just said, but that sounds so legit. So some of it's like, we don't want to make it sound really simple because then people think that they shouldn't have to pay us. It's never that simple. It's always more than complicated enough to justify getting paid. But unless, of course, it's really like, unless you find the injectors disconnected, in which case I don't think I'd fib that. I'd be like, hey, what's up with this car? Like, it came in for a misfire and the injector's disconnected. Are they setting me up? Is there a hidden camera? Am I going to be on the news? Like, I just come clean with that. But most of the time, like 99.9%, the car comes in broken and it's not something as simple as disconnected. It's more than complicated enough to get paid diagnosis. I would, if you don't agree, that's fine. We don't have to agree. But a plumber, right? If you have a leak and you see a leak coming from the roof and you call a plumber, you know they're going to charge you to come out and figure out what's leaking, right? Electrician, your breaker's tripping. You can't be like, hey, can you check my breaker? And they're not going to be like, oh yeah, let me come over and check it for you. Like, they're billing you. This is how the trades work. Like, you get charged for diagnosing the problem, right? So, but people are funny. They think like, oh yeah, you just like, you hooked up your fancy tool and then you looked and you found it was disconnected. Like, there's probably a much more complex diagnosis path. So high side drivers, just understand it's a positive side transistor. No big deal. Okay, field effect. We're going to get into the minutia, if you will, of transistors. A field effect transistor is kind of similar. It uses an electric field to shape the shape and conductivity of a channel of one type of charge carrier. So you're like, what? Field effect transistor has high resistance. It's another type of transistor. The thing is, it starts off with high resistance, and depending on how much voltage is applied to the gate, the conductivity is regulated. All right, so if you apply a little bit of voltage to the gate, you can have some current flow, but it's very high resistance. How would you make very low resistance through the transistor? You'd apply more current to the gate, more voltage to the base, right? So that's what we do. It's similar, right? So if we were to look at that on a diagram, the field effect would be like collector emitter, but sometimes we'll call this the gate. We can vary the amount of voltage that goes to this, and that will vary the amount of resistance going through here. So it's almost like if a switch was on or off, a field effect transistor is kind of more like a dimmer. We can ramp it up, we can ramp it down, we can fine tune the current flow through a field effect transistor. Okay, make sense? So it's similar, and we will use some of these in. We'll use some in different electronics, but it's not going to be your generic like turning the headlights on and off. It's going to be maybe more like an amplifier or something. So you can see it's very similar. Collector, emitter, gate, collector, base, and emitter. But if you notice, it's the source. They're coming up this time. The drain is where they exit. And then the gate is like the base. This is what we're going to vary here, okay? So whatever, it's not, it's a similar concept. It's just variable with different terms. Now for ASE, I've never ever been asked a question on ASE about a field effect transistor. They may ask just a bit about a regular transistor, and it'd be a diagram probably more similar to this. You'd have to understand, if you don't have 5 volts here, that means you're not going to get ground at the motor. And if you do have 5 volts here, but you're not getting ground here, it could be something with the transistor, right? It's going to be like this. It's not going to be a FET. Cool. even though they're similar. And then there's a MOSFET, and a MOSFET is just metal oxide semiconductor field effect transistor. So you'll notice it's similar to the field effect, and this is really what made like the transistor radio. A MOSFET's a high efficiency. They're, for whatever reason, and actually the exact details I don't totally know, they're really good for radios and amplifiers. So just so you're familiar, if you ever see this term MOSFET, that's just the type of electronics they're using in the radio or the amplifier. Going to make a little cleaner. Like they can switch really fast. They can do high current loads, and they can use a very low current control on the gate. Other than that, I just see them as another transistor. Cool. They are 4-terminal. Right. Not a big deal. And then there's a couple more. Bipolar junction transistors, another type. So this is stuff where you guys are welcome to study it as much as you want, but this is not the highest priority. The difference between these transistors is not the highest priority. You just want to be a little familiar. So if somebody says, oh, that's got a MOSFET, you're not like, oh, what? Be like, oh, a MOSFET. Yeah, that's a type of transistor, and I think it's like more, it's good for radios. That's about the extent of what I would memorize. The BJT, the bipolar junction transistor, is going to be similar, but it's going to use 2 different types of semiconductors. And same, amplifier, could be a switch, could be an oscillator. Sometimes they're individual components, but a lot of times these are integrated with a integrated circuit, like part of a chip. To be honest, I'm not exactly sure what the benefit of this would be. I do know a little bit more about the insulated gate bipolar transistor, and the reason I know a little bit more about this is we use these in hybrid EV, gosh, I was going to say rectifier. I'm tripping a little bit. Battery. I'll think of the name in 1 second. Totally losing it. Solar using 2. Man, I'm really blanking. Inverter. Gosh, that was just, it was in there. It was locked out though. So when we're doing hybrid EV stuff, remember how I said it's kind of easy to make AC into DC using those rectifier bridges with the diodes? But in a hybrid EV, we do that, okay? That's not that hard. We're going to take our AC current from, let's say, the wall of your home while you're charging. We're going to have an onboard, it's kind of a rectifier really, but they may call it like just a charging module or something. But we're going to take that AC and we're going to rectify it into DC, and we're going to put that into the battery. It's an inverter or kind of a converter too. So AC to DC is not that hard. DC to AC is much tougher, right? So if we pack a bunch of energy in that battery because we charge it overnight, now you got a bunch of DC in your battery, but you put it in drive and you push the accelerator pedal, it's not the gas pedal. We need to take that DC, make it into AC because we need to run an AC motor. So just how I said, the alternator, this starts to spin as AC, we make it into DC. See, in a hybrid or an EV, we have a DC battery. We need to make it into AC, and that AC is going to drive the motor. Okay, those are AC motors. That's kind of crazy because we have, you remember the sine wave of AC? If we were to back way, way, way up, it's okay. I'm going to back up. This is worthwhile of a reverse. Here's our AC motors. I kept it really simple. Here's your AC waveform. We ramp it up, we ramp it down, it goes negative, we turn it around. This is your AC waveform. How the heck could we reproduce that? If we have a battery, we need to reproduce a clean, nice, exact waveform. That's going to be difficult to do. Makes sense? And that's kind of what this was really saying. We need to produce 3 of those, phase 1, phase 2, and phase 3. So the way we're going to do that with our inverter is a lot of times we'll use IGBTs. They're capable of switching very high current loads and voltages at very high frequencies. They're so rapidly, they can produce what? Sophisticated waveforms. And they use pulse width modulation technique. So they can actually switch on and off so fast, they can replicate that AC waveform. So an IGBT is a transistor, but it's a little bit more advanced to not just turn things on and off. It can turn on and off so fast, it'll actually replicate AC. So in the car, we take the DC, we make it into AC, we drive the motors. That'd be a good job for IGBTs. There's IGBTs in your transistors. They're expensive. Your inverter is going to be very expensive if it goes bad on a hybrid or EV. Also, solar, photovoltaic solar system. You got solar panels on the roof. They produce DC. The DC goes down into your inverter. The solar panels on your roof, they just produce whatever the sun is. They're not regulated. Like if you got more sun, they produce more. If you got less sun, they produce less. They're just raw. The solar panels just harvest as much as they can, send it down to the inverter. The inverter takes that and it can actually produce this complex waveform. And this complex waveform has to perfectly match your grid power to actually be clean enough to push back into the grid or to run all of your stuff. So the same concept of the hybrid inverter, the hybrid EV inverter, is the same as a solar inverter that would hang on the wall like this. That's like $2,500. It's mostly because it's got these IGBTs. And these make a lot of heat. So on an inverter for a solar system, they have fans. Ideally, honestly, if you're going to do a solar system someday, try to put that inverter inside or like on the north side of a wall where it's out of the sun, because these IGBTs make a lot of heat. When they start to make a lot of heat, too much heat, and they can't cool, it'll actually start to derate your production. It'll basically start to reject your solar panels because it's making too much heat already. So it's kind of crazy. In a car, you know what we do to keep them cool? Coolant. So EVs have coolant. They have a radiator. You're like, why is there a radiator in my electric vehicle? Those make heat. Go ahead.
You have a Model S, right?
Yes.
Have you ever got like the ESS power reduced like after you go RFP?
No.
That's why they do it how?
Most of the time, yes. Most of the time, so like, let's say generically, EV problem, if for whatever reason those IGBTs start to show too much heat, which by the way that we'd pick up with a thermistor, FYI, it'll a lot of times reduce your power, it'll reduce your charging rates. It sometimes will actually make it so your AC won't blow cold anymore because your DC battery has to power an AC powered air conditioning compressor, so that all has to go through the IGBTs. The IGBTs have to generate a waveform, right? So yeah, if these start to get hot, you'll lose all that stuff. So it's overheating. That's essentially that power, that power loss or inverter overheating. That's like the same as your engine overheating, like something's up. It could be as simple as coolant low, or a coolant pump is not circulating the coolant, or your radiator fan is not working, or your radiator's got blocked airflow. Like that's the same as engine overheating. A little different to diagnose, but same concept. So that's what the IGBTs will do. Cool. Enough about IGBTs. They're not really super complicated. And now the last bits are more about actuators or inductors. So like we talked about how we could put, this is mostly going to be on the output side, right? We've talked some about outputs, but some of it's been sensors. Let's say that we needed to control this blower motor. Here's how we would control it with electronics. Be worth tracing. Red, let's do highlighter. And let's do color red. If you look, we got positive coming down here, right? I went a little too far there. All right, and then I can also tell you from the battery, positive is going to be here. And then I can tell you currently, we've got ground here. Oops, wrong color. Thought I clicked green. We've got ground here. We got ground here. We need, you know what we need? We need ground to come up to this point, don't we? So how would we do that? You guys agree we need green to go to that heater relay to close this switch, right? How do you think the AC control ECU could provide a ground? I will redraw this to make this so simple that you're going to be embarrassed. That's a switch. All right, so if I showed you this as a switch, you'd have been like, oh, you need to close the switch, right? That's what the ECU needs to do. The ECU needs to close this switch. You're welcome to pretend that there's switches in there, but you know there's not, right? What is probably inside the ECU? It's not going to be like a switch, but what can work kind of like a switch? Transistor is going to be in there. Yep, so if we have a transistor, that would more be like, remember how it had the little symbol and it had the little base over here and then it had the little symbol like that? We would just literally provide, this is probably going to be an N, P, and an N, right? So if the little ECU printed circuit on the computer chip sends a P on the base, now it's going to make a connection to the N, and guess what's going to happen? Now ground is going to come up to here, right? So can you see the role of the ECU? The ECU provides the ground. The ECU provides the ground by means of a switch, which is really a transistor. So let's say you were diagnosing this vehicle and the heater relay wasn't clicking and you're like, oh, it's got 12 volts here, but you check here and it has no ground. You'd probably need to come down here and check. And if the ground is not coming out of the ECU, you're troubleshooting the transistor. Technically, you could also have it where the ECU is not getting ground. Like this ground actually goes to chassis, right? So the way we diagnose it, it's not all that different. You just have to be comfortable with not being able to go inside of the module because we don't do that. You can't break the thing open and be like, oh, it's good, but now it's broken, so you need it, right? So like, you got to be good with, let me check the ground here, let me check the ground right here, and if it's not making ground here, it's inside. But what if that transistor were to give ground here, but the ground never made it up to here? Bingo, that would just be a wire, right? So like I started the lesson with, customer rolls up with a crank no start. Like a lot of the customer's concerns come down to these concepts. Is the thing getting what it's supposed to have? Yes. If the thing gets what it's supposed to have, but it doesn't work, the thing is no good. But if the thing doesn't get what the thing is supposed to have, what is it missing and where is it missing it from, right? So like in this case, the AC ECU, all it does is give ground or it doesn't give ground. It's that simple through a transistor. Transistors can fail. Not often, but they can. All right, but that's it. That's not all. Now that we got 12 volts in ground, what's going to happen? This, we'll use the pen. And we will change to red. Is going to go over, right? Because it's attracted to the magnetic field. We agree? And then this is now closed. What's that mean is going to happen to that positive voltage? It's going to go down like this. Bingo. Power the motor. But wait, that motor needs one more thing. That motor's got positive now. What else does it need? Well, guess how? This AC control ECU had a transistor. Well, this blower motor controller is also going to have a transistor, and this transistor has to actually pulse the ground to the blower motor. Now, the reason that I use this is, just so everybody knows, if you see this on the bottom of the slides, this is a slide that I made to supplement and add, to the generic material I get from the textbook. This is two modules in play. So if you have a blower motor in op, it could be the fuse, the relay, this wire, this wire, this wire, that wire, that wire, or that wire, but it could also be the AC control ECU or the blower motor controller. If you guess, and the motor itself, if you guess wrong on everything, you could probably spend like $3,000 fixing this blower motor concern. You can't just go shotgun and stuff. It's not, every year you can shotgun less and less because there's more and more computerization and more expensive parts to guess wrong. Make sense? So if we looked in here, this one has what we'll call a blower transistor. And the blower transistor, what it does, it's interesting, it actually pulses this ground. And if it gives the blower motor a lot of ground, it's going to go fast. But if it only pulses a little bit of ground, it's going to go slow. So the reason we have the blower motor controller here is because we're going to use one of those transistors. Maybe it's even I don't even know, it could be a BJT, it could be a MOSFET. I think it's a MOSFET on those, a lot of them. But it's going to pulse it in a way to control its speed, so we no longer need what we used to, which is a blower motor resistor. We used to put blower motor resistors to slow it down. Now we'll just pulse a transistor and that'll control it. So technically, when we turn this blower motor on, it's getting 12 volts, but the ground is being pulsed. A lot of ground, speed up, a little ground, slow down. Cool, so it gets a little complex, but transistors are running the show here, which is pretty normal. All right, not horrible, not horribly complicated. And that's kind of the point, is everything we learned about transistors and some what we learned about diodes and some what we learned about resistors and some what we learned about capacitors, that all comes together in the control module, right? The control module is the thing that it's the computer, right? It's an electronic device that controls one or more electrical systems. So in that blower motor, there was two control modules. In the example I gave earlier of the injector, that's the ECM controlling the injector. But if you wanted to add to that, a lot of times they have some sort of anti-theft module or immobilizer, where if you don't put the key in and turn it, or the key's not correct, or you try to break in, I mean, not you, somebody else, of course. Someone breaks in and they bust the lock cylinder out of it with a hammer, and then you just try to turn it with a screwdriver. The immobilizer ECU could be like, wait a minute, that's not the key, that's a hammer. Hello, ECU, don't send any power to the injectors, the car won't start. Make sense? So like, now we're talking about modules on modules on modules communicating to make it what it is, what you want, or what it's supposed to be, or, you know what I'm saying? It gets a little IT-ish, right? Because what if you have one module not communicating with the other modules? Now you're troubleshooting network issues, but that's the way it works. Cool, so a lot of this types of stuff. And then another thing that we spend a little bit of time on, but not yet, is the modules need to monitor input from sensors and circuits, process that, all that information it gets, and then send output commands to actuators, electrical devices, etc. The simple one I gave you was, remember that little circuit board? Are the lights in auto position, yes or no? Is it dark enough, yes or no? If the lights are in auto and it's dark, what should it do? Turn on the automatic headlights, right? Right now, we're mostly just talking about the parts, but later you need to understand that concept really well. And it's all part of it's going to use all the things we talked about. So this part tends to be a little bit like, I'm so tired of hearing about components, although we're going to be done with it in a few minutes. and then we're not going to really talk about them as components anymore. We're going to talk about them as systems. And when you look at the system, you have to understand what the component does and how it does it to understand the system. But you got to know the components first, right? So like this whole system, you could look at a diagram and you could see sensors, switches, transistors, all sorts of stuff, and you have to know what all those things do. And it's sometimes a little hard to tell. So here's your example of a module. I don't know what it is. Maybe this is an ECM, engine control module. I don't know. But you got the printed circuit board. You got all these transistors. Transistors are most likely in the chips, in the chipset. It looks like we got a couple capacitors, definitely a bunch of resistors, all sorts of stuff happening there. If you diagnose the vehicle as a bad low side driver, that's a transistor on the ground side. Where is it? I don't know. I really don't know. I have no idea where it's at. Maybe it's in here. Maybe it's in here. Honestly, I have no idea. I just know for sure it's a problem inside the ECU. I'm getting a whole ECU, putting a whole ECU in there. What I can't do is be like, well, let's try the computer first, because if that customer turns on you, and they will, they'll be like, hey, you put a computer and it didn't fix it, I'm not paying. You'd be like, that computer was $700, and then there's labor, and it's $1,000, and they'll be like, I'm not going to pay for that. You may or may not win that in court. It depends on the details as to like what you said to the customer. Technically you're allowed to guess. If you don't want to diagnose this and you're like, you know what, let's just guess. If you call the customer and you're like, hey, you need a computer, and they're like, why? And you'd be like, well, I can't tell you for sure that's the problem, but we need to start there because it makes the most sense and whatever. If that customer agrees, technically you'll probably win in court, and they'll probably make the customer pay you. But if you tell the customer, yeah, you need a computer, and they say that's going to fix it, and you'd be like, yep, nah, you're going to lose, especially if you don't have a very clear diagnostic path. How did you know it was a computer? Well, I Googled it. You lose. How'd you know it was a computer? Well, it was a guess. You lose, right? If you're guessing, you better tell them you're guessing. At which point, if you're guessing, you can't really be charging diagnosis. You can't do both. But if you say it's a computer and they say how did you know? You say like, on terminal number 27, there was supposed to be a ground pulse for the injector, and I probed it and there was no pulse for the injector, and therefore I determined it's the transistor, the low side driver for the injector. You win. I'd go with that. You know, and they hire professional experts to come and analyze the court cases, so that'd be legit. Of course, then you wouldn't be in court because it would have fixed the car, so kind of keeps you out of there. Right, and here's like an example. This is an integrated circuit chip. I don't know what's in there. There's some stuff in there. It's probably transistors and maybe resistors and maybe some things, right? But what I do know is there was a electrical engineer in my last electrical class, and he didn't know how to apply it to repair like me, but as far as what's in these chips and how and why, like that guy was way above me because that's what he does. All he does is design these systems. He told me he was making a crankshaft position sensor that had an integrated chip in there, and it had 3,000 tests he had to perform. 3,000 tests on the printed circuit. At this temperature, at this thing, in this condition, in that condition. So he's doing massive amounts of, he was working on this chip for months. And then if it passes all the tests, they put it into production, and then they pretty much let China produce it. But the people who design it and engineer it are here. And so it was really interesting talking with him about just how much stuff is going on in there. Like, I don't know the details. I really don't. His was kind of special because it's a Hall effect crankshaft position sensor, which there's quite a bit of electronics in there, but that wasn't even an ECM. That was a sensor with 3,000 tests. It's pretty nuts. So pretty wild. Okay, and so again, this can perform so many things. It can do so much stuff. So if you look at this, it looks tiny, but you understand that's like got a lot of power to switch things on and off and do things. You can imagine why we no longer want a bunch of little switches. The more we can go to this, the more stuff it can do. So if you want, remember when we were talking about the timer delay relays? If you want to turn your key off and have your headlights stay on, you can get a mechanical relay that you can wind up and it'll stay on for a while or something. Like, what a joke. I would run it through this. This, you could customize it. If you wanted, this probably has the ability to make your headlights turn off in 1 second, 2 seconds, all the way up second by second, up to probably hours long. It can probably look at your battery voltage. If your battery voltage goes low, turn your headlights off as a battery saver. It can have your headlights turn on and off when you lock or unlock it. It can have your headlights turn on and off. They can probably have your LEDs in sequence build up as you're charging at the EV charging station to show you charge from a distance while you're at Chick-fil-A, looking at it with your binoculars. Like, what's my percentage of charge? Like, you could do tons of stuff as soon as you go, bless you, with it, with any sort of a chip. Imagine there's going to be dozens, hundreds, thousands of circuits in there. So this is the way it's going to go, which makes our job harder to diagnose, just the way it is. It's going to be that way. Now this is the actual processor. So when we say the CPU, this one actually does the processing of information. So you guys would know, like, you get the latest phone and it's got the whatever Snapdragon thing or something. I don't even know what the latest terms are, but your RAM or your processing power is going to come from this. And you could have a problem in there. And that's not something that we change. That's a whole ECU replacement. Cool. So obviously the newer cars are going to have faster and faster ECUs. But they're in there. And how we work on it is like this. So this might be an ECM. This is actually a transmission control module. I can recognize that. This, I think, is an old ignition control module. This actually probably is an inside ECM. This might be an outside. You can actually tell it had sealant all over it. You know, so all these are ECMs or ECUs. They're processors in a way, but they can vary depending on system by system. Like, for example, sometimes what's frustrating, the transmission control module oftentimes is located inside the transmission. So that's kind of a bummer. You can't just like access it easily. You got to drain the fluid and drop the pan and then you can look at it, right? But that's just the way it is. Same with, like, if it's the driver's door module, that's going to be probably behind the panel, etc. But that's how it looks. And then, you know, here's a bunch of sensors. So essentially, when we get into the diagnosis, it's going to be very electrical based, but it's going to be specifically applied to that system. Cool. So we'll go over it electrically. We'll talk about the different tools to be used. Mostly our go-to for this class is going to be the DMM. The meter, the multimeter, the DVOM, if you will, digital voltometer. That's going to be the go-to. Towards the end, we'll do a little bit with the oscilloscope. In the beginning, last week, we did a little bit with the test light. That's probably about it. The test light be good for that 71 Chevelle. Not real great for this. Go ahead.
Back on a couple pages back, you said something about just the CPU.
Uh-huh.
Replace that whole units that we...
All right, see this little chip? Yeah, we're going to do this whole box right here. So if it has any problem in there at all, it's the whole entire assembly. So picture it, if it's a desktop, you pull the cords out the back, you take the whole big thing, you throw it in the garbage, and you bring a whole new one in like that. But the cool thing is, like with some of these, they don't need to be programmed, but with some of them, they do. So you can't just like jam an ECM in, and that's actually, I think it's right up in here in one of these pages. If you put a new ECM in, here you go, you may need to perform programming because a lot of times they come blank, right? So if that body control module fits 10 different vehicles, you may need to say, does this vehicle have power windows, power locks? Does it have keyless entry? Does it have a power lift tailgate? Does it have all these options? Does it have a sunroof or not, or a moonroof? If you put it in there, it's probably, in some cases it will, but in a lot of cases it's not ready to function. It has no operating system, basically. Like, it's like you put a new PC in, boom, but it doesn't have Windows on it yet. You got to actually upload that stuff. So if we go and we replace this, we'll most likely need to use the scan tool and upload the software into it. The challenge is, where do you get the actual software from, right? And so the by the book way is, this is mostly done at dealerships. So I would log in with my username and password. I'd say I'm going to do an ECU programming. What's the VIN? What's the information? What details? What options or whatever? And then it'll say, okay, download this file. And I'll be like, click. That file will get downloaded into my scan tool or my laptop. I go over to the car, I plug it into just to the regular DLC where we hook up a scan tool. I put the car on the battery charger to maintain voltage, a very clean battery charger. If your battery goes dead in this process, you know what a brick is, right? Because that's what you're going to get. And I can tell you firsthand exactly what happens when the battery goes dead, or when the porter walking through the bay, cutting through, kicks the cord out in the middle of programming. It's done. I need a new ECM. They're like, why? And I'm like, porter was cutting through and kicked the cable. And then they're like, put up cones and stuff. And I'm like, all right, fine. But like, don't you think everybody here should understand, if you see a cable running from the computer to the car, don't trip on it because it could cause. All right, fine. I'll put up cones. You want me to put up do not touch? What else would you like me to do to ensure this doesn't happen again? And in the meantime, the porter still knows nothing. But that's just how the business runs. Nah, it's kind of weird. Like, you could try, of course, but all you can do to reboot is take power away and plug it back in. No, mine was dead. Tried to get it back, tried to get it back, tried to get it back. I have had a couple where the programming failed, and then I was able to get it restarted, but most of the time, no, they're done. If it doesn't go through, you're done. So when these come blank, you got to have a way to get the software. You got to be careful uploading it. If you don't work at the dealership, sometimes you can buy a subscription to the softwares for all the different cars, but it's expensive. Other times I've seen people at independent shops where they will just pay a one-time fee for that software alone. It might be like $50, and they'll just get that software, boom, and then they could upload it. But you got to have a programming tool to actually write it. So changing a module like one of these is not as simple as you just unplug it and you slam it in there. It used to be, back in the day, a little more simple, but now they're finding ways to use this module on a lot of models, and you have to write the program for it. So doing a module is expensive, and it's also something that a lot of shops can't do themselves. Or, not to say they can't, but they're not going to do a subscription for a module for just your car. Like, they'd have to have a regular business to justify the subscription. Or what I've also seen, you guys can keep this in mind if you're interested in this. There's a guy in Temecula. He is a programmer. That's what he does. He has a bunch of scan tools. He has the subscription to all the different makes. And if you replace a module, he doesn't put them in. You put it in, you call him, he shows up. He's like, what year, make, model? He has the subscription. All he does all day long is upload software. And then he'll pull out, go to another. So he's mobile, and he keeps all the tools in his car, and he programs for a bunch of shops in Temecula. So that was that's a cool little go-to guy. And then there's another option sometimes where you can order the new module and give them the VIN and information, and they'll pre-program it, and they'll ship you one ready to plug in. That's also a possibility. They also do things where you can mail it to them, and they'll bench program it and send it back. So programming these, there's a bit of a, I don't know, it's a bit of its own little challenge. Cool, so we'll talk a little bit more about the sensors at another time when it's a little more controlled. So like, here's even a microcontroller. This would be a module. So maybe this is just something for the radio or the climate control or power windows. They do have microcontrollers that can be sort of universal, but they'll have them do certain things, like a programmable logic controller. They'll say, if you have voltage on terminal A and voltage on terminal B, send a ground out on terminal C or whatever. They can be kind of generic and they can do some functions. But for us, we don't really deal with these. Like the manufacturer would set these up and the supplier would build them into a box. You probably never see it in this form unless you disassembled it. But they may very well have those in this box though. Cool, so kind of interesting. And then we talked about like delay circuits. Remember, it could be mechanical, but with delay circuits, that's all very programmable once it's in a programmable, like an actual chipset. Cool. And then here's one thing we talked about. If you remember back here, remember this motor? How we could control the speed of this motor? We used to have resistors, but now we can do stuff like this. So your computer can actually make these waveforms. This would be 25% duty cycle. See, it's only got ground a quarter of the time. 50% would be half the time. 75% would mean 3/4 of the time it's got ground and then a quarter of the time it doesn't. Right? So once we get into modules, we can do a lot of stuff with controlling speed or time or whatever. It's not just on and off. And so that's what we were showing you with that blower motor control. It generates these. The challenge is when it generates this, you can't see this on your meter. You're generally going to go to an oscilloscope. You're going to actually have to verify that the module's creating this waveform and that it looks right. And if it's not, then you might have to do more troubleshooting. But if it is, you'd be like way back here, you'd be like, is this module doing its job, yes or no? Well, right here, it would be an actual waveform. You couldn't just see if it has ground. You'd have to scope it and see if it's making the correct square wave like one of these, okay? So just so you know, once you get into diagnosing a computer-controlled circuit, it can be a little bit more complicated. It's not a big deal. I'll show you how to do it. But it's a good one for you. And that's the duty cycle. And pulse width modulation is similar. But if we look at duty cycle, you're looking at 25% on, 75% off, 25% on, 75% off. Pulse width modulation looks at the amount of time. So it'll be milliseconds. Maybe this is 10 milliseconds. This is 5 milliseconds. This is 2 milliseconds. So similar, but the computer does all those, okay? Whoops, I went just a bit too far. But otherwise, you guys made it. It's intense, huh? All right, let's make our plans. So it's a pretty, I've got a pretty easy lab for you, but I'd say today'd be good. If you guys want to grab a nice proper lunch, that would be fine. If anybody wants to get the party started earlier,